The loneliest galaxies in the universe. Here is a peaceful thought to begin with. Somewhere in the darkness of space, there may be a galaxy shining so far from every neighbor that its stars seem to have the entire universe to themselves. Hi everyone, and welcome to Sleep and Learn. Tonight, let your thoughts drift far beyond the familiar spiral arms of the Milky Way, beyond crowded galaxy clusters and glowing rivers of stars. We are traveling towards some of the quietest places in existence, the enormous cosmic voids that stretch between the great structures of the universe. At first, a cosmic void may sound like a region containing absolutely nothing. But the truth is far more interesting. Voids are not perfectly empty. They are vast areas where matter is much more thinly spread than usual. Inside them, galaxies are rare, distances are enormous, and the darkness between objects can extend for tens or even hundreds of millions of light years. Imagine the universe as an immense three-dimensional web. Along its glowing threads, galaxies gather in groups, clusters, walls, and filaments. At the intersections of these threads, thousands of galaxies may live close together, pulled by gravity into enormous communities. Between the filaments lie giant, bubble-like regions containing far fewer galaxies. These are the cosmic voids. Together, the filaments, clusters, walls, and voids form what astronomers call the cosmic web, the largest known pattern in the universe. From a great enough distance, galaxies do not appear randomly scattered. Instead, they resemble tiny lights resting along the strands of an endless celestial spiderweb. And yet, hidden inside some of the darker spaces between those strands, a small number of galaxies continue to shine. These are known as void galaxies. A void galaxy may be separated from its nearest large neighbor by millions of light years. It can spend most of its existence without experiencing the dramatic collisions and gravitational disturbances that regularly reshape galaxies in crowded environments. In a rich galaxy cluster, life can be chaotic. Galaxies rush past one another at tremendous speeds. Their gravitational fields stretch spiral arms, disturb clouds of gas, and sometimes pull entire streams of stars into intergalactic space. Two galaxies may merge, creating bursts of star formation or feeding the supermassive black holes at their centers. A void galaxy experiences something very different. Its surroundings are calm. There may be no massive neighbor nearby to twist its shape. No frequent collision may arrive to compress its gas. No crowded cluster may strip away its outer atmosphere. Instead, the galaxy evolves slowly, guided mostly by its own gravity, its supply of gas, and the faint influence of the cosmic web around it. This makes void galaxies extremely valuable to astronomers. They are like natural laboratories where researchers can study how galaxies grow when the universe leaves them mostly undisturbed. One famous example is MCG plus 0102-015, a galaxy located in a remarkably empty region of space. It is so isolated that NASA once described a striking possibility. Had the Milky Way occupied a similarly lonely location, early astronomers might not have discovered other galaxies until the arrival of powerful modern telescopes. The night sky beyond our own galaxy could have appeared almost completely empty. Consider what that would feel like. For most of human history, people looked upward and saw the pale band of the Milky Way, scattered stars, planets, and the occasional comet. But they could also observe faint patches of light that eventually proved to be distant galaxies. In a deep cosmic void, many of those faint patches might be missing. An intelligent civilization living there could study astronomy for centuries without realizing that the universe contains vast clusters filled with thousands of galaxies. Their picture of the cosmos might begin as one of profound isolation. Only after inventing extremely sensitive instruments would they discover the truth. Their lonely galaxy was not the entire universe, but a tiny island hidden inside a dark cosmic ocean. Another beautiful example is KK246, a small irregular galaxy within the local void, a relatively empty region near our own cosmic neighborhood. KK246 contains young blue stars, glowing pink regions of active star formation, and dark lanes of dust. Although it lives in a sparse environment, it is not frozen or lifeless. New stars are still being born inside it. This is one of the most relaxing surprises about void galaxies. Isolation does not always mean inactivity. A lonely galaxy can still gather gas. Its internal clouds can still cool and collapse. Stars can still ignite, shine, age, and gently enrich their surroundings with heavier elements. Even without frequent collisions, the slow rhythms of galactic life continue. Within a cloud of cold hydrogen, gravity draws atoms together. The cloud becomes denser. Its center warms. After millions of years, pressure and temperature rise high enough for nuclear fusion to begin. A new star appears, a small point of light inside one of the emptiest regions of the known universe. Around that star, disks of dust and gas may form planets. Somewhere in a void galaxy, there could be worlds orbiting quiet suns beneath a sky almost entirely free of distant galactic light. Their nights would be dark, clear, and unimaginably deep. Void galaxies also challenge the simple idea that empty regions contain no structure. Astronomers now understand that smaller filaments, faint gas streams, dwarf galaxies, and invisible concentrations of dark matter may exist inside voids. These hidden structures are far more delicate than the great filaments surrounding galaxy clusters, but they may still guide gas and matter toward isolated galaxies. Even the emptiest cosmic regions may contain a faint internal web. Dark matter, which does not shine or absorb light, provides much of the gravitational framework. Ordinary matter, mostly hydrogen and helium gas, can slowly flow along this framework. Where enough material gathers, a small galaxy may form. This means that a void is not simply a hole cut into the universe. It is a quieter landscape with its own geography, history, and evolution. And perhaps that is the most comforting way to imagine it. The universe does not require crowded places to create beauty. A galaxy does not need thousands of neighbors to produce stars. Even inside a region defined by emptiness, gravity can gather scattered matter, gas can become luminous, and tiny islands of light can continue shining for billions of years. So, as you relax, picture one of these distant void galaxies. See it floating alone in an immense darkness, its faint spiral arms turning slowly. Blue stars glitter along its edges. Small clouds of pink hydrogen glow where new suns are being born. Around it stretches an ocean of space so wide that light itself may travel for millions of years before reaching another major galaxy. There is no rush there. No crowded cluster surrounds it. No bright neighboring galaxy dominates its sky. It simply turns quietly through the darkness, carrying billions of stars on their long and peaceful journey through time. And in the next part, we will travel even deeper into the cosmic web to discover how these enormous voids were created, and why the universe grew into a pattern of glowing filaments surrounding vast seas of darkness. How the great cosmic voids were born. Long before galaxies existed, the universe was not perfectly smooth. It contained tiny differences in density, small places with slightly more matter, and others with slightly less. Those small differences eventually became everything. In the earliest moments after the Big Bang, the universe was hot, bright, and filled with rapidly moving particles. Matter was spread almost evenly across space, but not with complete perfection. Some regions contained a little more material than average. Others contained a little less. At first, these differences were incredibly small. They were not yet galaxies, stars, or empty cosmic deserts. They were only faint variations in density, like gentle ripples across a vast and glowing ocean. But gravity is patient. Where matter was slightly denser, gravity began pulling in more material. As those regions gained mass, their gravitational attraction became stronger. More gas and dark matter flowed toward them, allowing them to grow even denser over time. Meanwhile, regions that began with slightly less matter slowly lost material to their surroundings. Matter was drawn away from them and pulled toward the denser regions nearby. Over billions of years, this process created the great contrast we see today. Dense regions became galaxy clusters, walls, and filaments. Less dense regions expanded and developed into cosmic voids. In this way, the emptiest places in the universe were not created by explosions that pushed matter away. They formed gradually as gravity gathered matter elsewhere. Imagine a field covered with a very thin layer of morning mist. If parts of the mist slowly drift towards certain areas, those areas become thick and visible, while other regions become clearer and more transparent. The cosmic web developed in a similar way, although on a scale almost impossible to imagine. Dark matter played a central role in this process. It does not emit light, so astronomers cannot see it directly. Yet its gravity helped shape the universe before ordinary matter formed the first stars. Dark matter gathered into invisible halos and long filaments. Ordinary gas followed these gravitational pathways. Where enough gas collected, stars and galaxies eventually formed. The result was a universe that resembled a three-dimensional network. Clusters of galaxies appeared where multiple filaments met. Long walls of galaxies stretched between them. Vast voids opened in the spaces enclosed by these structures. Cosmic voids can be tens of millions of light-years wide. Some of the largest are far greater. Within them, the average density of matter may be only a fraction of that found in ordinary regions of the universe. Yet voids continue to change. Because they contain less matter, their gravity is weaker than that of the surrounding filaments and clusters. Matter near the edges can continue moving outward, away from the center of a void and toward denser structures. As a result, cosmic voids may slowly expand relative to the structures around them. This does not mean they are expanding into some external emptiness. Instead, the internal distances within them grow as the universe itself expands and as matter continues to migrate toward denser regions. Voids can also merge. Small empty regions may grow and join together, creating larger and more complex voids. Over cosmic time, the universe becomes increasingly structured, with matter concentrating into thin networks while the spaces between those networks become more dominant. In fact, most of the volume of the universe is occupied by voids. The galaxies, clusters, and bright filaments that appear so important to us occupy only a relatively small portion of cosmic space. The great majority is made of these enormous low-density regions. This is one of the most surprising facts about the large-scale universe. When people imagine space, they often picture stars everywhere. But on the grandest scales, emptiness is the rule, and concentration is the exception. The luminous universe is shaped like a delicate skeleton surrounded by darkness. Still, even this darkness contains subtle patterns. Not all voids are identical. Some are nearly spherical, while others are stretched or irregular. Some are surrounded by dense galaxy walls. Others lie within larger underdense regions. Some contain a few isolated galaxies, while others are almost completely free of visible objects. Astronomers study these differences because voids preserve valuable information about the history of cosmic expansion. Since voids contain relatively little matter, their evolution can be less complicated than that of crowded galaxy clusters. This makes them useful for testing ideas about gravity, dark energy, and the growth of structure. Dark energy is the name given to the mysterious influence associated with the accelerating expansion of the universe. Its effects become especially interesting in low-density regions, where the gravitational pull of matter is weaker. Because cosmic voids are so empty, they may offer a particularly clear environment for observing how cosmic expansion changes over time. Researchers map voids by measuring the positions and distances of enormous numbers of galaxies. When plotted in 3 dimensions, the galaxies reveal great gaps between filaments and clusters. Some surveys have mapped millions of galaxies, creating astonishing images of the cosmic web. In these maps, each galaxy appears as a tiny point, yet together the points form sweeping arcs, knots, walls, and empty bubbles. It is like seeing the architecture of the universe. The pattern did not appear all at once. It developed slowly, beginning with tiny variations in the young cosmos and growing under the influence of gravity for nearly the entire age of the universe. Every galaxy cluster, every filament, and every void carries a memory of those earliest fluctuations. Even the faint afterglow of the Big Bang, known as the cosmic microwave background, contains traces of the unevenness from which the cosmic web eventually formed. The temperature differences within this ancient light are extremely small, but they reveal where matter was slightly denser or thinner when the universe was still very young. Those delicate patterns later grew into structures billions of light-years across. A tiny early imbalance became a galaxy cluster. Another became a long filament. And a region with slightly less matter became a vast cosmic void. There is something peaceful in the slowness of this transformation. Nothing needed to hurry. Gravity worked quietly across immense periods of time. Matter drifted, gathered, and rearranged itself. The universe slowly changed from a glowing, nearly uniform beginning into a landscape filled with galaxies and enormous dark spaces. So now, imagine looking at the universe from a distance far beyond any individual galaxy. You would see countless points of light arranged along thin, curving threads. Between them would be huge, shadowy spaces, gently expanding and merging as cosmic time passes. Inside one of those spaces, a few lonely galaxies may continue to shine. They are not mistakes in the pattern. They are survivors of the same ancient process, small islands of matter that remained within regions from which most material had gradually flowed away. And in the next part, we will visit these isolated galaxies more closely to discover how life in a cosmic void can shape their size, color, gas supply, and unusual evolution. How galaxies evolve in cosmic isolation. A galaxy living inside a cosmic void may seem lonely, but its quiet surroundings can tell us something extraordinary. Sometimes, the absence of neighbors changes everything. In crowded regions of the universe, galaxies rarely evolve in complete peace. They pass close to one another, exchange gas, distort each other's shapes, and sometimes merge into larger systems. A galaxy in a dense cluster may be pushed, stretched, stripped, or transformed by the environment around it. Void galaxies follow a different path. Because they live in regions where galaxies are widely separated, they experience fewer major collisions and fewer powerful gravitational encounters. Their evolution is often slower, gentler, and more dependent on what is happening inside them. This does not mean that every void galaxy looks the same. Some are graceful spirals. Others are small irregular systems with no clear shape. Many are dwarf galaxies containing far fewer stars than the Milky Way. A few appear surprisingly bright and active, despite living in some of the emptiest regions of space. The most important difference is that void galaxies are less affected by external pressure. In a large galaxy cluster, a galaxy may move through extremely hot gas that fills the space between neighboring galaxies. This hot environment can sweep away the galaxy's own cold gas, much like wind removing smoke from a moving object. Cold gas is essential for making new stars. When a cluster galaxy loses that gas, its star formation may slow or stop. Over time, it can become redder because its young blue stars die while older, cooler stars remain. Void galaxies are usually protected from this kind of stripping. There is no dense ocean of hot cluster gas surrounding them, so they may keep their hydrogen for much longer periods. For this reason, many void galaxies are rich in gas. They often contain large reservoirs of neutral hydrogen extending far beyond their visible stars. This gas can act as fuel for future generations of stars. Even a small galaxy may continue forming new suns for billions of years if its supply is used slowly. This helps explain why many void galaxies appear blue. Young, massive stars emit strong blue and ultraviolet light. Although these stars live for only a short time compared with smaller stars, their presence reveals recent star formation. A blue galaxy is often a galaxy that is still actively creating new stars. In isolation, this process can continue at a calm pace. A void galaxy may not experience the spectacular starburst triggered by a major collision. Instead, it can form stars gradually in scattered clouds. One region brightens, then another. Small groups of young stars appear along spiral arms or inside irregular patches of gas. The galaxy does not erupt all at once. It flickers quietly across cosmic time. This slow evolution may allow some void galaxies to preserve features that would have been erased in busier environments. Their disks can remain thin. Their spiral patterns may stay relatively undisturbed. Their outer gas can stretch into faint structures that survive for long periods. Yet isolation is never absolute. Even inside a cosmic void, small galaxies can interact with one another. A void may contain faint groups, pairs of dwarf galaxies, or thin chains of matter that are difficult to detect. Two small systems may still pass close enough to disturb their gas and trigger new star formation. This reveals an important truth. A void is not empty in the same way as a completely blank room. It is more like a quiet countryside compared with a crowded city. The distances are greater, and encounters are less frequent, but subtle relationships still exist. Some void galaxies have small companions. Others show warped disks, unusual star-forming regions, or streams of gas that may be signs of past interactions. These features remind astronomers that even a very isolated galaxy has a history. Another mystery concerns how quickly void galaxies mature. In theory, matter gathers more slowly in low-density environments. This suggests that galaxies inside voids may form later or develop more gradually than galaxies in dense regions. Some astronomers describe this as delayed evolution. A void galaxy may remain small, gas-rich, and actively star-forming for a longer time. It may look younger than a similar galaxy in a cluster, even if both began forming billions of years ago. But the picture is not simple. Some void galaxies contain old stars, showing that star formation began early. Others have experienced several generations of stellar birth and death. A galaxy can live in a quiet region and still possess a long and complex history. The difference may lie not in when its first stars appeared, but in how slowly its material was used. Imagine two households given the same amount of firewood. One burns it quickly in a powerful blaze. The other keeps a small fire glowing through many nights. A crowded galaxy may experience collisions that rapidly convert gas into stars. A void galaxy may preserve its fuel and use it more gently. Both produce light, but their rhythms are different. Dwarf galaxies are especially common in discussions of void evolution. These small systems may contain only a few million or a few billion stars, compared with the hundreds of billions that can inhabit a large galaxy. Their weak gravity makes them sensitive to supernova explosions, radiation, and gas loss. When massive stars die, they release energy into the surrounding gas. In a dwarf galaxy, this energy can push material outward or even remove some of it entirely. Because void dwarfs often have few neighboring galaxies to provide fresh material through mergers, their survival depends strongly on whether they can retain or replace their gas. Some appear to succeed. They continue producing stars in small bursts separated by long quiet periods. Their star formation may stop temporarily, then begin again when gas cools and settles back toward the center. A dwarf galaxy can seem almost asleep for hundreds of millions of years before new stars awaken inside it. Void galaxies may also be more chemically primitive. Stars create elements heavier than hydrogen and helium. When they die, these elements are released into space, enriching the gas from which later stars and planets form. A galaxy that has created fewer generations of stars may contain lower amounts of oxygen, carbon, iron, and other heavy elements. Astronomers refer to this abundance as metallicity. Some isolated dwarf galaxies have extremely low metallicity. Their gas resembles the material that existed in the younger universe, before countless generations of stars had enriched space. These galaxies are not truly untouched relics from the beginning of time, but they may offer a rare glimpse of how star formation behaves in relatively simple conditions. Low metallicity gas cools differently from gas rich in heavy elements. It may form stars in unusual ways, and the stars themselves may become hotter or more massive. This makes void galaxies valuable for understanding the earliest eras of galaxy formation. The black holes at their centers may also evolve differently. Large galaxies often contain supermassive black holes. In crowded environments, mergers can deliver gas toward the center and feed these objects, causing them to shine as active galactic nuclei. Void galaxies experience fewer major mergers, so their central black holes may receive less fuel. Some may remain relatively small and quiet. Yet astronomers have found active black holes even in isolated galaxies. Gas does not require a major collision to move inward. Internal structures, such as bars and spiral arms, can gradually guide material toward a galaxy's center. Small interactions with dwarf companions can also disturb the gas. Even in solitude, a black hole can awaken. This is why void galaxies are so fascinating. They allow scientists to separate the influence of a galaxy's internal processes from the influence of its surroundings. When astronomers observe a galaxy in a cluster, many forces may be acting at once. A void galaxy offers a cleaner experiment. Its color, shape, gas supply, and rate of star formation may reflect more of its own natural development. But perhaps the most beautiful aspect of void evolution is its quiet persistence. A small galaxy may spend billions of years drifting through a region with almost no bright neighbors. It may slowly turn its gas into stars, one cloud at a time. Some stars live briefly and explode. Others shine gently for longer than the current age of the universe. Planets may form around them. Moons may orbit those planets. And all of this may happen within a galaxy so remote that its nearest large companion is millions of light-years away. The galaxy does not know that it is isolated. Its stars continue to shine. Its gas continues to move. Gravity continues shaping its spiral arms and holding its worlds in orbit. From our perspective, it may appear lonely. From within, it would be an entire universe of light. As you relax, imagine floating above one of these quiet galaxies. Its disk glows softly beneath you. Blue stars sparkle in loose groups, while reddish older stars fill the center. Beyond the edge of the galaxy, darkness stretches farther than the mind can comfortably measure. There is no crowded cluster nearby, only a faint cosmic web, a few distant dwarf companions, and an ocean of peaceful space. And in the next part, we will explore the invisible structures that make even this quiet life possible. Dark matter halos, hidden filaments, and the slow rivers of gas flowing through the cosmic void. The invisible rivers of the cosmic web. Here is a calming thought. Even in the emptiest parts of the universe, matter is still moving quietly, following invisible paths through the dark. A cosmic void may look like an enormous empty bubble, but it is not cut off from the rest of the universe. Thin streams of gas, small dark matter filaments, and faint gravitational structures can pass through it like delicate threads. These structures are difficult to observe because most of them do not shine. Stars are bright. Galaxies can be photographed. Hot gas may glow in X-rays. But much of the universe is made of material that produces little or no visible light. Dark matter is one of the most important examples. Astronomers cannot see dark matter directly because it does not appear to emit, reflect, or absorb light in the usual way. Its presence is known mainly through gravity. Galaxies rotate as though they contain far more mass than their visible stars and gas can explain. Galaxy clusters bend light from more distant objects, revealing large amounts of unseen matter. The large-scale cosmic web itself also appears to have grown around an invisible framework dominated by dark matter. Every void galaxy is believed to exist inside a dark matter halo. This halo may extend far beyond the visible edge of the galaxy. The stars and glowing gas occupy only the central region, while the unseen halo forms a much larger gravitational envelope. Without this hidden structure, many small galaxies might not remain together. A dwarf galaxy has relatively weak gravity compared with a giant spiral like the Milky Way. Supernova explosions, stellar winds, and radiation from young stars can disturb its gas. Yet a surrounding dark matter halo can help hold material near the galaxy and prevent all of it from escaping into space. In this way, something invisible may protect the visible galaxy. Dark matter halos also attract fresh gas. Hydrogen and helium moving through intergalactic space can be pulled toward a halo by gravity. As the gas falls inward, it may become denser, lose energy, and eventually settle into a rotating disk. There, after a long period of cooling and compression, part of the gas may begin forming stars. This process can happen without a collision. Galaxies do not always need to merge in order to gain new fuel. They may be supplied by slow streams of intergalactic gas flowing along the cosmic web. These streams are sometimes described as cosmic rivers. The phrase is poetic, but it also captures something real. Matter does not move randomly through the universe. Gravity guides it toward denser regions. Gas tends to flow along filaments, from quieter areas into galaxies and clusters. The largest filaments connect enormous groups of galaxies. But computer simulations suggest that smaller and much fainter filaments may exist inside cosmic voids. A void may therefore contain its own miniature web. Instead of massive galaxy clusters, this web may be traced by dwarf galaxies. Instead of brilliant walls containing thousands of systems, it may consist of narrow chains of gas and dark matter that are almost impossible to detect. At the intersections of these small filaments, a void galaxy may grow. This idea changes the way we imagine cosmic emptiness. A void is not a featureless black sphere. It may contain layers of structure too faint for ordinary telescopes to reveal. There may be filaments within filaments. The great cosmic web can be compared to the branches of a tree. Large branches divide into smaller branches, which divide again into delicate twigs. The largest structures are easy to notice. The smallest may remain hidden until more sensitive instruments are developed. Void galaxies can act as markers of those invisible twigs. When astronomers map the positions of isolated dwarf galaxies, they sometimes find that the galaxies are not distributed completely at random. They may form faint lines, sheets, or small groups. Gravity has arranged them. Their positions may reveal hidden concentrations of dark matter beneath the visible universe. Gas behaves differently depending on its temperature. Some intergalactic gas is extremely hot. Other material is warm and diffuse. The gas most useful for star formation is usually cooler and denser, although cooling in space is a slow and complex process. A galaxy can receive gas through what astronomers call cold accretion. The word cold is relative. The gas may still be far warmer than anything found in an ordinary room, but it is cooler than the shock-heated material surrounding massive galaxies and clusters. In smaller dark matter halos, streams of relatively cool gas may penetrate deep into the galaxy. This gas can provide fresh hydrogen for star formation. It may also contain fewer heavy elements than the gas already inside the galaxy. When such material mixes with the galaxy's existing gas, it can change the chemical composition of future stars. This may help explain why some void galaxies are metal poor. In astronomy, Metals are all elements heavier than hydrogen and helium. Oxygen, carbon, silicon, and iron are all considered metals in this broad sense. The first generations of stars formed mostly from hydrogen and helium. Heavier elements were created later inside stars and during stellar explosions. Gas arriving from the wider cosmic web may be less chemically enriched than gas that has been recycled through several generations of stars. A void galaxy receiving this fresh material may therefore continue producing stars with relatively low metallicity. The gas does not always arrive smoothly. It can fall inward unevenly, forming clouds, streams, or warped outer disks. Some galaxies contain hydrogen structures that extend far beyond their visible starlight. These large gas envelopes can be mapped using radio telescopes. Neutral hydrogen emits a particular radio signal known as the 21 centimeter line. By observing this faint emission, astronomers can detect gas that would otherwise remain invisible. A galaxy that appears small in visible light may turn out to have an enormous hydrogen disk. This is especially important in voids, where faint gas structures may contain more mass than the visible stars suggest. The hydrogen can reveal bridges between small galaxies, asymmetrical clouds, or long tails created by weak interactions. Even isolated galaxies may not be completely alone. A tiny companion that is too faint to see easily may pull on the gas of a larger galaxy. A dark matter subhalo containing few or no stars may also disturb the outer disk. These subtle interactions can compress gas and trigger new star formation. A galaxy may suddenly produce a group of bright blue stars, not because it collided with another large galaxy, but because a faint invisible structure passed nearby. This possibility is part of the mystery of dark galaxies. A dark galaxy is a theoretical or candidate object containing gas and dark matter but very few stars. Because stars provide most of the visible light in a galaxy, such an object would be extremely difficult to find. Some unusual hydrogen clouds have been proposed as possible dark galaxies, although many later turn out to be debris, tidal structures, or gas associated with ordinary galaxies. Still, the idea remains scientifically interesting. Could the cosmic voids contain many dark matter halos that never formed enough stars to become visible? According to models of galaxy formation, the universe may contain far more small dark matter halos than the number of dwarf galaxies we can observe. This is related to a long-standing puzzle, sometimes called the missing satellites problem. Simulations often predict many small halos orbiting larger galaxies, yet fewer luminous satellite galaxies are detected. Some halos may simply be too small to hold gas. Others may have lost their gas early in cosmic history. A few might contain stars so faint that they have not yet been discovered. Inside voids, hidden halos could be even harder to detect because there are fewer bright objects nearby to reveal their gravitational effects. A dark halo might drift for billions of years without ever becoming a true galaxy. To form stars, gas must overcome several obstacles. It must gather in sufficient quantity. It must remain inside the halo. It must cool. It must become dense enough to collapse. And it must survive heating from ultraviolet radiation and energetic stellar events. During the early universe, intense radiation changed the condition of intergalactic gas. This period, known as reionization, may have prevented many small halos from forming large numbers of stars. Their gravity was simply too weak to hold hot gas. Some of these halos may still exist today as invisible remnants. If so, the apparently empty regions of space may be filled with unseen gravitational islands. They would not shine like ordinary galaxies. They would not appear in photographs. Yet they could influence gas, bend the paths of passing objects, or leave subtle patterns in the movement of visible matter. Astronomers search for these effects in several ways. They study the rotation of galaxies. They measure the movement of hydrogen clouds. They examine how light from distant quasars is absorbed by gas between the quasar and Earth. A quasar is an extremely bright galactic center powered by matter falling toward a supermassive black hole. Because quasars can shine across enormous distances, their light acts like a beam passing through the universe. When that beam crosses a cloud of hydrogen, certain wavelengths are absorbed. By studying these missing wavelengths, astronomers can detect gas that emits almost no light of its own. In this way, a distant quasar can illuminate the invisible structure of a cosmic void. Each absorption line is like the shadow of a hidden cloud. Many such measurements together can reveal the distribution, temperature, and chemical composition of intergalactic gas. Scientists also use computer simulations to explore this hidden universe. Simulations begin with conditions resembling the early cosmos. They include gravity, dark matter, gas dynamics, star formation, and the energy released by stars and black holes. As the simulated universe evolves, a cosmic web appears naturally. Dense regions collapse into clusters. Filaments connect them. Voids open between the filaments. Inside the voids, smaller structures form. When simulated void galaxies are compared with real ones, astronomers can test whether their theories are accurate. Do the galaxies contain the right amount of gas? Are they forming stars at the expected rate? Are their dark matter halos large enough? Do hidden filaments appear where observations suggest they should? Every answer helps refine our understanding of how visible matter and invisible gravity work together. There is something deeply peaceful about these cosmic flows. Gas may travel for millions or billions of years before reaching a galaxy. It moves through darkness along a path shaped by gravity. Eventually, part of it may enter a cloud, collapse, and become a star. Atoms that once drifted almost alone through a void may one day shine inside a sun. Around that sun, some of the heavier elements created by earlier stars may become rock, ice, atmosphere, or ocean. The journey from intergalactic gas to a planet can be unimaginably long. Yet the process begins with a quiet movement through the cosmic web. So, as you rest, picture the invisible landscape surrounding a void galaxy. A broad dark matter halo embraces its stars. Thin streams of hydrogen approach from the distance. Smaller halos drift silently nearby. Faint filaments cross the void like threads of glass that can be felt only through gravity. Nothing appears to move quickly, but over millions of years, the gas comes closer. It circles the galaxy, cools, and settles into its outer disk. Then, somewhere inside a quiet cloud, gravity begins gathering the material together. A new light is preparing to shine. And in the next part, we will enter those isolated clouds to discover how stars are born in environments where gas is scarce, pressure is low, and the nearest large galaxy may be millions of light years away. Star formation in the quietest galaxies. In one of the emptiest regions of the universe, a small cloud of gas can remain dark for millions of years, and then, very slowly, begin creating a star. Star formation inside a void galaxy is both familiar and unusual. The basic process is the same throughout the universe. Gas gathers under gravity, becomes denser, cools, and eventually collapses. At the center of the collapsing cloud, temperature and pressure rise until hydrogen nuclei begin to fuse. A new star is born, but the environment surrounding that process can be very different. In a crowded galaxy cluster, stars may form after powerful collisions compress enormous clouds of gas. Spiral galaxies can pass close to one another, sending shock waves through their disks. Large quantities of gas may be driven inward, creating brilliant episodes of star formation. Void galaxies usually live more quietly. They are less likely to experience major collisions, so their gas is often compressed by gentler forces. A spiral arm may slowly gather material. A small companion may disturb the outer disk. A stream of fresh hydrogen may arrive from the cosmic web. Turbulence inside a cloud may create a dense pocket where gravity can take control. The result is often star formation on a smaller scale. Instead of producing thousands of massive stars at once, a void galaxy may create scattered groups of young stars across its disk. One region may glow brightly for a few million years, while another remains dark and inactive. This patchy pattern is common in small irregular galaxies. Such galaxies may not have the smooth spiral arms seen in the Milky Way. Their stars and gas can be distributed unevenly, creating a shape that appears disorganized. Yet inside this irregular structure, star formation follows local conditions with remarkable precision. Where the gas becomes dense enough, stars appear. Where it remains thin, the galaxy stays dark. Most of the visible material in a young star-forming region is hydrogen. Hydrogen is the simplest and most abundant element in the universe. Under ordinary conditions, it can exist as neutral atomic gas, but inside colder, denser clouds, hydrogen atoms can join together to form molecules. These molecular clouds are the primary birthplaces of stars. They are cold by astronomical standards, often only a few tens of degrees above absolute zero. Their low temperature allows gravity to overcome the random motion of the gas more easily. Dust also plays an important role. Cosmic dust is made of tiny solid particles containing elements such as carbon, silicon, oxygen, and iron. Although dust makes up only a small fraction of a galaxy's mass, it helps gas cool and provides surfaces where hydrogen molecules can form. But many void galaxies contain relatively few heavy elements. If a galaxy has experienced only limited star formation, fewer generations of stars have had time to create and release carbon, oxygen, and other elements. This means the galaxy may contain less dust than a more evolved system. With less dust, molecular hydrogen can be more difficult to form and protect. Ultraviolet radiation from young stars can break molecules apart. Dust usually absorbs some of this radiation, shielding the gas inside a cloud. In a metal-poor void galaxy, the protection may be weaker. This creates an interesting challenge. A galaxy can have plenty of atomic hydrogen, yet still form stars inefficiently because only a small amount of the gas becomes cold and molecular. This may be one reason why some void galaxies preserve their gas for so long. They are not necessarily empty of fuel. Instead, much of the fuel remains in a state that is difficult to convert into stars. Imagine a vast storage room filled with wood that is too damp to burn. The material is present, but the conditions are not yet right. In a similar way, a void galaxy may contain an enormous reservoir of hydrogen while producing only a few new stars each year, or even fewer. The Milky Way is thought to form roughly a small number of solar masses of stars per year. Many dwarf void galaxies form stars at rates far below that, sometimes only a tiny fraction of the mass of the Sun each year. This does not mean they form part of a star. Rather, the rate is averaged across long periods of time. A galaxy may create several stars in one region and then remain relatively quiet elsewhere. Star formation often happens in bursts. A small galaxy can spend hundreds of millions of years forming stars very slowly. Then a cloud becomes unstable, perhaps because of an internal shock, a gas flow, or a weak interaction. For a short period, the star formation rate rises. Young blue stars appear. Their radiation ionizes the surrounding hydrogen, causing it to glow in pink and red colors. These glowing clouds are known as emission nebulae, or H2 regions. An H2 region is created when ultraviolet light strips electrons from hydrogen atoms. When the electrons later return, the atoms release light at particular wavelengths. To an astronomer, these regions are bright signs of recent stellar birth. In a small void galaxy, a few glowing H2 regions can dominate the entire visible appearance of the system. The oldest stars may be faint and widely spread, while the young regions shine intensely. This can make the galaxy look as though most of its stars are young, even when an older stellar population is hidden underneath. Massive young stars are especially bright. They can be many times more massive than the Sun and thousands or millions of times more luminous. But their lives are brief. While the Sun may shine for about 10 billion years, the most massive stars can survive for only a few million years before exhausting their nuclear fuel. They then explode as supernovae. In a large galaxy, one supernova has only a local effect. In a tiny dwarf galaxy, it can influence a significant part of the entire system. The explosion drives a shock wave through the surrounding gas. It heats the material, pushes it outward, and mixes newly created elements into the interstellar medium. Several supernovae occurring close together can create a huge cavity known as a superbubble. These bubbles can expand across hundreds or even thousands of light years. They may sweep gas into dense shells, where a second generation of stars can later form. This creates a cycle. Stars are born from gas. The most massive stars release energy. That energy disturbs nearby gas. Some gas is blown away, while some is compressed into new clouds. Star formation can both destroy its own birthplace and create the conditions for future stars. In a dwarf void galaxy, this balance is delicate. If supernovae inject too much energy, gas may be pushed beyond the galaxy's central regions. Because the galaxy's gravity is weak, part of the material could escape. This would reduce future star formation. But if the dark matter halo is massive enough, the gas may remain gravitationally bound. It can rise above the galactic disk, cool slowly, and fall back later. Astronomers sometimes call this a galactic fountain. Gas is lifted by stellar energy and later returns like a slow cosmic rain. The complete journey may take hundreds of millions of years. When the gas falls back, it can mix with fresh material arriving from outside the galaxy. This mixture may then form another generation of stars. Void galaxies may repeat this cycle many times. A burst of activity is followed by silence. Gas cools. Another burst begins. The pattern continues across billions of years. This rhythm helps explain why a small isolated galaxy can contain both very old stars and extremely young ones. Its history is not a single continuous flame. It is more like a series of candles being lit at long intervals in a dark room. Some isolated galaxies contain star-forming regions far from their centers. These outer regions are especially mysterious because the gas there may be very thin. Traditional models often suggest that gas must reach a certain density before widespread star formation can begin. Yet ultraviolet observations have revealed young stars beyond the bright optical disks of some galaxies. These extended ultraviolet disks show that star formation can occur in surprisingly sparse environments. The process may begin inside small dense pockets hidden within a much larger diffuse gas cloud. Even if the average density is low, local compression can create conditions suitable for collapse. Fresh gas flowing in from the cosmic web may also collide with material already orbiting the galaxy. Where the streams meet, pressure rises. The collision may be gentle by human standards, taking place over millions of years, but it can still help trigger the birth of stars. A warped outer disk may be another clue. If incoming gas approaches from a different direction than the galaxy's existing rotation, it can form tilted rings or bends. These structures may later become sites of star formation. The orientation of new stars can preserve a memory of how the gas arrived. In this way, a galaxy's shape becomes a record of invisible cosmic flows. Some void galaxies are known for having extremely low amounts of metals while still actively forming stars. These systems are especially valuable because they resemble, in certain ways, galaxies from the early universe. In the young cosmos, nearly all galaxies were metal-poor. Their first stars formed before many generations of supernovae had enriched the gas. Astronomers cannot observe every small galaxy from that distant era in detail. But nearby metal-poor dwarfs provide a kind of natural laboratory. They allow scientists to study star formation in chemically simple gas at much closer distances. The comparison is not perfect. A modern void galaxy exists in an older universe filled with radiation and enriched material. Still, some of its internal conditions may echo those found billions of years ago. The stars created from metal-poor gas may behave differently. Gas with few heavy elements tends to cool less efficiently in certain temperature ranges. Clouds may need to become denser before collapsing. The resulting stars may be somewhat more massive on average, although this depends on many complex factors. Massive stars also emit intense ultraviolet radiation. This radiation changes the gas around them, creating ionized bubbles that can expand through a small galaxy. In low-density surroundings, the radiation may travel especially far. A single young star cluster can therefore influence a large volume of space. The radiation can delay star formation in one region by heating the gas, while compressing another region at the edge of the expanding bubble. Again, destruction and creation are connected. Black holes may also influence star formation, although most dwarf void galaxies do not contain the kind of powerful active nucleus seen in giant galaxies. If a small central black hole begins consuming gas, it may release radiation or jets. This energy can heat the nearby material and reduce star formation, or in some cases compress gas and help create stars. However, in many isolated dwarfs, ordinary stars and supernovae are probably the dominant sources of feedback. The word feedback is used because stars affect the gas that later forms more stars. Without feedback, gas might collapse too quickly, creating far more stars than astronomers actually observe. Stellar radiation, winds, and supernovae regulate the process. A galaxy is therefore not simply a container where gas turns into stars. It is a changing ecosystem. Gas cools and collapses. Stars form. Energy returns to the gas. Some material escapes, some remains, and some is recycled. Heavy elements gradually accumulate. The entire appearance of the galaxy changes. In a quiet void, this ecosystem can develop with relatively little influence from larger neighbors. That isolation gives astronomers a clearer view of the internal processes. It becomes easier to ask whether star formation is driven by gas density, dark matter, turbulence, chemical composition, or the energy of previous stars. Of course, the answer is usually a combination of all these factors. There is no single clock controlling a galaxy. Instead, countless local events overlap across enormous scales of time and distance. One cloud collapses. Another is dispersed. A supernova explodes. A stream of hydrogen arrives. A dark matter halo holds the material together. And slowly, the galaxy continues. Even the quietest galaxy is never truly still. Its stars orbit the center. Gas clouds collide. Magnetic fields twist through the interstellar medium. Radiation crosses the disk. Invisible particles pass through stars and planets. But from a distance, the whole system appears peaceful. Its changes are measured in millions of years. A bright young cluster that seems permanent to us may be only a brief flash in the life of the galaxy. A dark cloud that appears empty may already be beginning the slow collapse that will create future suns. Perhaps planets can form around some of those suns. Dust particles collide inside disks surrounding young stars. Tiny grains become pebbles. Pebbles become larger bodies. Over millions of years, worlds may emerge. Even a chemically primitive galaxy can contain the ingredients for planets, though the types of planets and their abundance may differ from those in richer environments. Rocky worlds require elements such as silicon, iron, magnesium, and oxygen. These elements are created by earlier generations of stars. A very young or extremely metal-poor galaxy may have fewer materials for building Earth-like planets. But after enough stars live and die, the necessary elements can gradually accumulate. The history of planets begins inside stars. Every atom of iron in a rocky world was produced through ancient nuclear processes. Every carbon atom in a living cell was once part of a star or stellar explosion. In a void galaxy, that enrichment may happen slowly. But slowly does not mean never. Across billions of years, even a small isolated system can transform simple hydrogen and helium into a richer collection of elements. Its first stars prepare the material for later stars. Its earliest supernovae make future planets possible. The darkness becomes more complex with every generation. So, as you rest, imagine a small cloud of hydrogen near the edge of a lonely galaxy. The cloud is almost invisible. It is surrounded by a darkness so deep that no large neighboring galaxy can be seen. Very gradually, the cloud cools. Its densest center begins to shrink. Gravity gathers more atoms inward. The temperature rises. A disk forms around the collapsing center. Then, after an immense and silent preparation, fusion begins. A new star opens its light inside the void. It may shine for millions or billions of years. It may warm a family of planets. Its light may never reach a crowded galaxy until long after the star itself is gone. Yet for the quiet island of matter around it, that light becomes a new beginning. And in the next part, we will explore the smallest inhabitants of these empty regions, dwarf galaxies that may preserve ancient gas, hidden histories, and some of the most mysterious structures in deep space. Dwarf galaxies hidden inside the voids. Sometimes the smallest galaxies carry the oldest stories. Far from the bright crowds of galaxy clusters, deep inside cosmic voids, tiny dwarf galaxies drift through the darkness. Some are so faint that they can be difficult to distinguish from the empty sky around them. Yet these small systems may preserve clues about the early universe, the behavior of dark matter, and the long, quiet history of star formation. A dwarf galaxy is much smaller than a giant spiral such as the Milky Way. While the Milky Way contains hundreds of billions of stars, a dwarf galaxy may contain only a few billion, a few million, or even fewer. Its visible body can be so faint that a large telescope must collect light for many hours before its structure becomes clear. But small does not mean simple. Dwarf galaxies can contain old stars, young stars, gas clouds, dark matter, star clusters, and sometimes black holes. Their shapes may be round, irregular, stretched, or barely organized at all. Inside cosmic voids, dwarf galaxies are especially important because they may evolve with fewer disturbances from larger neighbors. In crowded environments, small galaxies are fragile. A massive galaxy can pull stars and gas away from them. A galaxy cluster can expose them to hot gas and powerful tidal forces. Over time, these effects can strip a dwarf galaxy almost bare. But in a void, a dwarf may remain relatively untouched. It can keep more of its gas. It can avoid repeated gravitational encounters. It may continue forming stars slowly for billions of years. This makes void dwarfs valuable records of natural, isolated evolution. Some of them may resemble galaxies that formed in the early universe, not because they are young, but because their development has been slow. They may still contain large amounts of hydrogen and only small quantities of heavier elements. Their stars may be arranged in irregular groups rather than smooth spiral patterns. Their dark matter halos may dominate almost every aspect of their structure. In many dwarf galaxies, the visible stars represent only a small fraction of the total mass. The rest is thought to be dark matter. This invisible material creates the gravitational field that holds the galaxy together. Without it, the stars and gas may not have enough mass to remain bound. The dominance of dark matter makes dwarf galaxies especially useful for testing ideas about the nature of this mysterious substance. Astronomers can measure how quickly stars and gas move through a dwarf galaxy. If the visible matter cannot explain those motions, an unseen source of gravity is required. Some dwarf galaxies appear to contain hundreds or even thousands of times more dark matter than visible matter. They are among the most dark matter-dominated objects known. In a cosmic void, such a galaxy may exist almost entirely as an invisible halo with only a faint sprinkling of stars at its center. This raises a fascinating question. How many dark matter halos are hiding in voids without any visible galaxy at all? Computer models suggest that the universe should contain enormous numbers of small halos. Yet telescopes detect far fewer dwarf galaxies than some simulations predict. One explanation is that many halos never formed stars. Their gravity may have been too weak to collect and retain enough gas. Radiation from the early universe may have heated the gas and prevented it from settling. Supernova explosions may have removed the little material that did gather. These halos could remain dark for billions of years. They would not appear in ordinary images. They might contain no stars, or only a few too faint to detect. They would be gravitational structures without visible light. Void regions may be ideal places to search for such hidden objects because the environment is quieter. Yet the same emptiness makes the search difficult. There are fewer bright background sources. Distances between objects are large. The gravitational influence of a small dark halo may be extremely subtle. Astronomers therefore search indirectly. They study unusual movements in gas clouds. They look for faint distortions in the shapes of visible galaxies. They examine how light from distant objects bends as it passes through space. Gravitational lensing can reveal mass even when that mass is dark. According to general relativity, gravity bends the path of light. A large galaxy cluster can produce dramatic arcs and multiple images of background galaxies. A dwarf-sized halo creates a much weaker effect, but with precise measurements, it may still leave a detectable signature. Another way to find faint dwarf galaxies is through neutral hydrogen. A galaxy may contain too few stars to be obvious in visible light while still holding a large cloud of gas. Radio telescopes can detect the 21-centimeter signal produced by neutral hydrogen. Some surveys have discovered hydrogen-rich objects with only faint stellar counterparts. These systems may be nearly dark galaxies, very young-looking dwarfs, or gas clouds influenced by nearby structures. Determining their true nature requires careful observation. A cloud of hydrogen is not automatically a galaxy. To qualify as a galaxy, it should generally be gravitationally bound and associated with a dark matter halo. But gas can also be pulled from ordinary galaxies during interactions, creating isolated-looking clouds that are actually debris. In a void, where interactions are rare, a detached gas cloud may have a different origin. It could be material slowly condensing inside a dark halo. It could be a stream flowing through the cosmic web. Or it could be the remains of an ancient encounter between two tiny galaxies. Every possibility tells a different story. Some void dwarf galaxies are called blue compact dwarfs. These are small galaxies with bright central regions of active star formation. Their young stars produce strong blue light, making the galaxy appear unusually vivid despite its small size. A blue compact dwarf may contain an older population of faint stars beneath the bright central burst. This means the galaxy itself is not necessarily young. Instead, it may be experiencing a temporary period of intense star formation after a long quiet phase. What triggered the burst? Perhaps fresh gas entered the galaxy. Perhaps two small dwarfs passed near one another. Perhaps internal turbulence compressed a large cloud. The cause may be hidden in faint structures around the galaxy. Deep images sometimes reveal extended halos of older stars, distorted outer regions, or tiny companions that ordinary surveys miss. This is why longer and more sensitive observations often change our understanding of isolated galaxies. A galaxy that first appears completely alone may later be found to have several faint neighbors. The void is not empty. It is simply difficult to see. One of the most intriguing types of small galaxy is the ultra-diffuse galaxy. An ultra-diffuse galaxy can be similar in size to the Milky Way but contain far fewer stars. Its light is spread so thinly that the galaxy appears almost transparent. Many ultra-diffuse galaxies have been found in clusters, but similar faint systems may also exist in less crowded regions. Some appear to contain large amounts of dark matter. Others may contain surprisingly little, which has created scientific debate. Because these galaxies are so faint, their mass is difficult to measure. A small error in the estimated motion of their stars can produce a large difference in the calculated dark matter content. Still, ultra-diffuse galaxies remind us that size and brightness are not the same thing. A galaxy can cover an enormous area while remaining nearly invisible. Inside a void, such a system might blend smoothly into the darkness. Its stars could be separated by great distances. From a planet inside it, the night sky might look less crowded than the sky seen from Earth. Even within the galaxy itself, isolation could exist on a smaller scale. Dwarf galaxies also help astronomers understand how the first stars enriched the universe. A very metal-poor dwarf may contain gas with only a tiny fraction of the heavy elements found in the Sun. These galaxies offer clues about the earliest stages of chemical evolution. When the first stars formed, the universe contained almost no carbon, oxygen, iron, or silicon. Those elements were created later in stellar interiors and explosions. Each generation of stars changed the gas available to the next. In a small galaxy with slow star formation, this enrichment can happen gradually and unevenly. One region may contain gas enriched by a nearby supernova. Another region may remain chemically primitive. As a result, stars born in different parts of the same dwarf galaxy may have noticeably different compositions. Astronomers study their light to detect these differences. Every element absorbs and emits light at particular wavelengths. By separating starlight into a spectrum, scientists can identify chemical signatures and estimate how much of each element is present. The spectrum becomes a record of the star's birthplace. Iron can reveal contributions from certain kinds of supernovae. Oxygen may reflect the deaths of massive stars. Carbon and nitrogen can provide clues about earlier generations of stellar evolution. By studying many stars, astronomers can reconstruct the history of the galaxy. They may discover that star formation occurred in several bursts separated by long silent intervals. They may find evidence that gas was lost and later replaced. They may see that some of the oldest stars formed more than 10 billion years ago. A tiny dwarf galaxy can therefore preserve a timeline almost as long as the age of the universe. Some void dwarfs may also contain ancient globular clusters. Globular clusters are dense, spherical collections of old stars. A single cluster may contain hundreds of thousands of stars packed into a region only a few hundred light-years wide. In a faint galaxy, a globular cluster can represent a large portion of the total visible light. These clusters are relics of early star formation. Their ages and chemical compositions can reveal when the host galaxy first began creating stars. In some cases, the cluster survives even after much of the galaxy around it has been disturbed or lost. It is like a small archive of ancient suns. Another mystery concerns the centers of dwarf galaxies. Do they contain black holes? For a long time, supermassive black holes were associated mainly with large galaxies. But astronomers have found evidence that some dwarf galaxies contain central black holes with masses far below those found in giant systems. These objects are sometimes called intermediate mass black hole candidates. They may help explain how the first supermassive black holes formed. Perhaps the early universe produced small black hole seeds. Some grew rapidly inside dense environments, eventually reaching billions of times the mass of the Sun. Others, especially in isolated dwarf galaxies, may have remained small. A black hole inside a void dwarf could therefore be a relatively unchanged remnant of an ancient population. It may spend most of its life quietly. Only when gas falls toward it does the black hole become visible, producing radiation from the hot material surrounding it. A faint active nucleus in a tiny isolated galaxy can be difficult to detect. Star formation also produces strong radiation, sometimes hiding the black hole signal. Astronomers use X-rays, radio waves, and detailed spectra to separate these sources. Each candidate offers another clue to the early growth of galaxies and black holes. Dwarf galaxies may also be shaped by invisible motions inside their dark matter halos. Different theories of dark matter predict slightly different distributions of mass. Some models produce steep concentrations near the center of a halo. Observations of certain dwarf galaxies instead suggest flatter central regions. This disagreement is known as the core cusp problem. One possibility is that repeated bursts of star formation alter the dark matter distribution. Supernovae move gas rapidly in and out of the center. The changing gravitational field may gradually push dark matter outward, creating a flatter core. Another possibility is that dark matter behaves differently from the simplest models. Void dwarf galaxies are useful for testing these ideas because their histories may be less disturbed by tidal forces from larger galaxies. If their central dark matter distributions can be measured accurately, they may help separate internal stellar effects from the fundamental behavior of dark matter itself. But accurate measurements are difficult. Dwarf galaxies are faint. Their stars move slowly. Gas can be disturbed by turbulence. The shape of the galaxy may be irregular. Science advances through these difficulties one careful observation at a time. A radio telescope maps hydrogen. An optical telescope measures starlight. A space telescope searches for faint old stars. A computer simulation tests whether the observed galaxy could form under known physical laws. Gradually, the hidden structure becomes clearer. There may be many more dwarf galaxies waiting to be discovered. New sky surveys are becoming sensitive to objects with extremely low surface brightness. Instead of searching only for bright points, astronomers can look for faint, diffuse patterns spread across large regions of the sky. Machine learning systems may help identify structures too subtle for quick human inspection. But every candidate must still be confirmed. A faint patch may be a distant galaxy, a cloud of dust in the Milky Way, scattered light from a bright star, or an artifact of the instrument. Finding a nearly invisible galaxy requires patience. And perhaps patience is the defining feature of dwarf galaxies themselves. They grow slowly. They form stars in small episodes. They can drift through emptiness for billions of years without merging into anything larger. Some may survive almost unchanged while great galaxies elsewhere collide, expand, and transform. Imagine a dwarf galaxy floating near the center of a cosmic void. It contains a few million stars, surrounded by a dark matter halo many times more massive than everything visible. Its oldest stars are dim and reddish. Near one edge, a small cloud of hydrogen is beginning to collapse. A handful of blue stars illuminate the gas around them. Beyond the galaxy lies an extraordinary darkness. The nearest large spiral may be so far away that its light appears only as a faint point. Yet inside this small island, gravity continues its quiet work. Stars orbit. Gas cools. Heavy elements spread from one generation to the next. A hidden black hole may rest at the center. The galaxy may seem insignificant beside the Milky Way, but it carries a complete history of cosmic evolution in miniature. It shows that the universe does not need grandeur to preserve mystery. Sometimes the faintest objects reveal the deepest truths. And in the next part, we will travel beyond the visible edges of these galaxies to search for even stranger inhabitants of the voids. Dark galaxies, starless halos, wandering gas clouds, and structures that may exist almost entirely beyond the reach of light. Dark galaxies and starless islands. Here is a strange but gentle idea to hold in your mind. Some galaxies may be almost completely dark, carrying gas and gravity through space without enough stars to make themselves visible. When we hear the word galaxy, we usually imagine light. We picture spiral arms glowing with billions of stars, bright clouds of gas, and a luminous center. Even a small dwarf galaxy is expected to contain at least a faint collection of suns. But light is only one part of a galaxy. Most of a galaxy's mass may be invisible. Dark matter forms a broad halo around the stars, while cold gas can extend far beyond the bright central region. In some unusual cases, the visible part may be so weak that the object appears to be little more than a drifting cloud. Astronomers sometimes use the term dark galaxy for a system believed to contain dark matter and gas but very few stars. A truly dark galaxy would be one of the quietest objects in the universe. It might possess enough gravity to collect hydrogen, yet fail to compress that gas into dense, cold clouds. It could orbit inside a void for billions of years without ever producing a large stellar population. Such an object would not look like an ordinary galaxy through an optical telescope. There might be no spiral arms, no golden center, and no blue clusters of young stars. Instead, astronomers would need to detect it through radio waves, gravity, or the influence it has on nearby matter. This makes dark galaxies extremely difficult to confirm. A radio telescope may discover a large cloud of neutral hydrogen in apparently empty space. At first, the cloud may seem like a galaxy with no stars, but later observations may reveal that it is actually gas pulled away from another galaxy during a collision. Other clouds may be part of long tidal streams, faint bridges, or the outer regions of galaxies whose stars are too dim to detect in early images. The universe can hide the origin of gas very well. To decide whether a hydrogen cloud is a dark galaxy, astronomers ask several questions. Does the cloud appear to rotate? Is it held together by its own gravity? Does it contain more mass than the visible gas can explain? Is there a dark matter halo around it? Could it have been torn from a nearby galaxy? Does deeper imaging reveal a faint population of stars? The answers are often uncertain. Gas can appear to rotate when it is actually moving along a stream. A cloud may look isolated because its connection to another object is too faint to see. What seems like dark matter may be the result of complicated motion rather than true gravitational support. For this reason, many dark galaxy candidates remain debated. Still, the idea is strongly connected to our understanding of galaxy formation. According to the leading picture, galaxies form inside dark matter halos. First, dark matter gathers under gravity. Gas then falls into the halo, cools, and eventually begins forming stars. But this sequence does not always reach its final stage. Some halos may be too small. Their gravity may not be strong enough to hold gas heated by radiation. Even when hydrogen enters the halo, it may remain too warm and diffuse to collapse. The object becomes a failed galaxy, not because it was destroyed, but because it never truly began to shine. The early universe may have created many such systems. After the first stars and galaxies formed, their intense ultraviolet radiation spread through space. This radiation ionized much of the intergalactic hydrogen during the era of reionization. Ionized gas is warmer and harder for small halos to capture. A massive halo can still pull the gas inward. A tiny halo may lose it or fail to collect it at all. As a result, many small dark matter structures may have remained starless. Cosmic voids could contain large numbers of these hidden halos. Dense regions eventually gather more matter, causing halos to merge and grow. Inside voids, growth is slower. Small halos may remain small for the entire age of the universe. Because there are fewer collisions, a starless halo may avoid being absorbed into a larger galaxy. It may continue drifting through the void as an invisible island of gravity. This possibility is fascinating because it suggests that the number of galaxies we see is not the same as the number of galactic structures that exist. The visible universe may be only the illuminated portion of a much larger dark population. Imagine a deep photograph containing a few faint dwarf galaxies surrounded by empty black space. That darkness may not be truly empty. Within it, there could be numerous halos with no stars at all. Some may hold thin clouds of hydrogen. Others may consist almost entirely of dark matter. They would be present, but hidden from every ordinary image. How could astronomers find them? One possible method is gravitational lensing. Mass bends the path of light. If a dark halo lies in front of a distant galaxy or quasar, it can slightly distort or magnify the background object. The effect of a small halo is extremely subtle, but precise observations may reveal irregularities in gravitationally lensed images. For example, a massive foreground galaxy can create several images of the same distant quasar. If a smaller dark halo lies near one of the light paths, that image may appear brighter, dimmer, or slightly displaced compared with predictions. The halo does not need to shine. Its gravity reveals it. Astronomers can also search for changes in cold streams of stars. Around large galaxies such as the Milky Way, thin streams are created when globular clusters or dwarf galaxies are pulled apart by gravity. Their stars continue moving along similar orbits, forming long and delicate structures. If an invisible dark matter halo passes through a stellar stream, it may create a gap or bend. The stream becomes a record of a hidden encounter. This method is most useful near large galaxies, not in the centers of distant voids. Yet it demonstrates how invisible structure can be detected by its influence on visible matter. Hydrogen provides another possibility. A dark halo containing neutral gas may emit the 21 centimeter radio signal. Large surveys can search wide areas of the sky for clouds without obvious stars. The most interesting candidates are isolated, massive enough to be gravitationally bound, and separated from known tidal debris. But even radio observations have limits. Very diffuse gas produces an extremely weak signal. If the cloud contains mostly ionized hydrogen, the 21 centimeter emission may disappear. A halo could therefore contain matter while remaining invisible to both optical and ordinary radio surveys. Background light can sometimes expose it. When light from a distant quasar passes through a gas cloud, atoms absorb particular wavelengths. This creates dark lines in the quasar's spectrum. These absorption lines can reveal gas too faint to detect through its own emission. A cloud inside a void may therefore announce its existence only as a tiny missing portion of light from an object billions of light-years behind it. The cloud itself remains unseen. We notice only its shadow. Some hidden systems may not be completely dark. Instead, they may contain a handful of stars spread over a vast area. These are sometimes described as almost dark galaxies. An almost dark object may be rich in hydrogen but extraordinarily inefficient at turning that gas into stars. Its stellar population can be so faint that only deep observations reveal it. The galaxy might contain millions of times the mass of the Sun in gas while producing very little visible light. Why does the gas not form more stars? One reason may be low density. Gas spread across a large region may never reach the concentration needed for widespread gravitational collapse. Another reason may be low metallicity. Without many heavy elements or dust grains, the gas may struggle to cool and create molecular clouds. Its dark matter halo may also have unusual properties. If the halo is broad and diffuse rather than centrally concentrated, the gas may never experience strong enough pressure near the center. The galaxy remains full of potential but nearly inactive. A small disturbance could change everything. If another dwarf passes nearby, gravity may compress part of the gas. A stream from the cosmic web may collide with the cloud. An internal instability may send material toward the center. Then, after billions of years of darkness, the object could begin forming stars. A few blue points would appear inside the hydrogen. The dark galaxy would become visible. This possibility raises a beautiful question. Can we ever observe a galaxy at the moment it first begins to shine? In reality, even the most primitive nearby galaxies usually contain older stars, showing that their history began long ago. Completely new galaxies are not expected to form commonly in the modern universe. But an ancient dark halo might experience its first substantial episode of star formation very late. It would not be a newly created halo. It would be an old structure undergoing a delayed awakening. Such an object could help astronomers understand the transition from darkness to light. There are also large hydrogen clouds known as high-velocity clouds around galaxies, including the Milky Way. These clouds move at speeds that do not match the simple rotation of the galactic disk. Some may be gas falling into the galaxy. Others may have been expelled by supernovae or stripped from smaller companions. A few could be associated with dark matter halos. Determining which explanation applies is challenging because distance is often difficult to measure. A small nearby cloud and a large distant cloud can produce a similar radio signal. Without knowing the distance, astronomers cannot accurately calculate its size or mass. This is one reason dark structures remain mysterious. We can detect a signal without immediately knowing the physical object behind it. Cosmic voids introduce another difficulty. Their galaxies are far apart. A hydrogen cloud may have no bright neighboring object that can help reveal its distance. The void itself provides few reference points. Still, the isolation can also be useful. In dense environments, tidal debris is common. Inside a deep void, a truly isolated gas cloud is less likely to have been recently stripped from a giant galaxy. If such a cloud appears stable and rotating, the possibility of a hidden dark matter halo becomes more convincing. Dark galaxies are not the only invisible structures in voids. Thin sheets of ionized gas may fill large portions of the space between visible galaxies. Small dark matter halos may form chains along faint internal filaments. Warm gas may flow outward from the center of a void toward its edges. Most of this matter is too diffuse to shine brightly. On the largest scales, the word empty becomes relative. A void contains far less matter than a cluster, but it can still hold countless particles, magnetic fields, radiation, neutrinos, and dark matter structures. Even a cubic meter of intergalactic space may contain a few atoms, depending on the region. That is almost nothing by earthly standards, yet across millions of light-years, those scattered atoms add up to an enormous amount of material. Emptiness can still possess mass. It can still have temperature. It can still change. One of the great mysteries of modern cosmology is the missing ordinary matter problem. Astronomers can estimate how much normal matter should exist from observations of the early universe. But when they count the stars, galaxies, and easily visible gas in the modern universe, some of that matter appears to be missing. A large portion is believed to exist as extremely diffuse gas between galaxies, especially in the warm-hot intergalactic medium. This material can have temperatures ranging from hundreds of thousands to millions of degrees. It may lie along the cosmic web in forms that are difficult to detect. Although much of it is associated with filaments outside void centers, the boundaries and faint internal structures of voids may also contain hidden reservoirs. Scientists search for this gas through absorption lines in ultraviolet and X-ray spectra. Again, distant bright objects serve as background lamps. The gas does not reveal itself by glowing strongly. It reveals itself by quietly removing certain wavelengths from passing light. There is something almost poetic about that method. We learn about hidden matter by studying what is absent. A faint line missing from a spectrum becomes evidence of a cloud no telescope has photographed. A slight bend in a beam of light becomes evidence of an invisible halo. A gap in a stream of stars becomes evidence that something dark passed through. The unseen universe writes its presence into the visible one. Dark galaxies also matter for theories of dark matter. The most familiar model is cold dark matter. In this picture, dark matter particles move relatively slowly compared with the speed of light when structures begin forming. This allows small halos to appear first and later combine into larger ones. The model successfully explains much of the cosmic web, but it predicts many small halos. If future surveys find large numbers of starless halos, this would support the idea that the halos exist but often fail to form galaxies. If far fewer halos are found than expected, scientists may need to reconsider how dark matter behaves or how small structures evolve. Alternative ideas include warm dark matter, self-interacting dark matter, and other possibilities. Each can change the predicted abundance or internal structure of small halos. Void environments are useful because small-scale structures there may be less affected by the complicated history of large clusters. A void can become a testing ground for invisible physics. Yet even the word dark can be misleading. A starless halo is not dark in every possible sense. It may contain a weak background of radiation. Gas may emit faint radio waves. Cosmic rays may pass through it. Dark matter particles, whatever they are, may interact in ways we have not yet discovered. Dark simply means that the object gives us little light to observe. It is not necessarily inactive. Gravity still works there. Gas still moves. Particles still collide. The halo may slowly grow as it captures matter from the surrounding void. Over vast periods, its future may change. Some dark halos could eventually merge with a luminous dwarf galaxy, adding mass without adding many stars. Others may approach the edge of a void and become part of a larger filament. A few may remain isolated almost forever. As the expansion of the universe continues, the distances between widely separated structures increase. In the far future, some objects may become even more isolated than they are today. A starless halo in a deep void could drift through darkness while distant galaxies gradually move beyond its observable horizon. Its history would continue without an observer. There might never be a star inside it to provide warmth or light. And yet it would still be part of the universe's structure, a quiet concentration of mass shaped by the same ancient fluctuations that formed galaxy clusters and stars. Consider the atoms in a dark gas cloud. Some may have existed since the first minutes after the Big Bang. They may never have entered a star. They may never have become part of a planet, ocean, or living cell. For nearly 14 billion years, they could have traveled through expanding space as simple hydrogen or helium. A few may finally drift into a dark matter halo. There they gather, very slowly. Perhaps they remain too thin to collapse. Perhaps one day they will cool. The future is uncertain, but the journey itself is extraordinary. Not every part of the universe must become luminous to have a history. Some matter spends its entire existence in silence. So, as you relax, imagine floating through the center of a cosmic void. At first, you see nothing around you. No bright spiral galaxy fills the distance. No crowded cluster glows ahead. But invisible structures are everywhere. A small dark matter halo passes quietly nearby. Within it, a thin cloud of hydrogen rotates too slowly to form stars. Farther away, another halo contains only a handful of dim red suns. Between them, warm gas follows a delicate filament toward the edge of the void. The darkness is not empty. It is filled with unfinished possibilities. Some structures may never shine. Others may be waiting for one gentle disturbance, one arriving gas stream, or one slow gravitational collapse. And in the next part, we will explore how these hidden galaxies and faint structures help scientists investigate one of the deepest questions in cosmology. where the cosmic voids contain clues about the true nature of dark matter and dark energy. What cosmic voids reveal about dark matter and dark energy? Here is a quiet mystery to consider. The emptiest places in the universe may help us understand the two most invisible forces shaping everything we see. Cosmic voids contain very few galaxies, but they are far from scientifically unimportant. In fact, their emptiness is precisely what makes them valuable. Crowded galaxy clusters are complicated. They contain enormous amounts of hot gas, countless interacting galaxies, powerful magnetic fields, active black holes, and deep wells of gravity. Many processes overlap, making it difficult to separate one effect from another. Voids are simpler. They contain less matter, fewer collisions, and weaker gravitational competition. This allows astronomers to study certain cosmic effects in a cleaner environment. Two of the greatest mysteries are dark matter and dark energy. Dark matter helps pull the universe together. Dark energy appears to push its large-scale expansion faster. Neither has been directly observed in the same way as a star, planet, or gas cloud. Their existence is inferred from what they do. Dark matter reveals itself through gravity. It affects the rotation of galaxies, the motion of galaxy clusters, the bending of light, and the formation of the cosmic web. Dark energy reveals itself through the expansion history of the universe. Distant galaxies appear to be moving away in a way that suggests cosmic expansion has accelerated over time. Voids exist between these two influences. They formed because gravity drew matter away from underdense regions and into surrounding filaments and clusters. But as the universe expanded, the low-density interiors of voids grew increasingly empty. Their evolution therefore depends on both matter and cosmic expansion. Imagine two neighboring regions in the young universe. One contains slightly more matter than average. The other contains slightly less. In the denser region, gravity slows expansion more strongly. Matter gathers, structures collapse, and galaxies form in larger numbers. In the underdense region, gravity is weaker. Matter moves outward towards surrounding structures, and the region expands more freely. Over billions of years, the difference becomes enormous. The dense region may become a galaxy cluster. The underdense region may become a void tens of millions of light-years across. Because dark energy becomes more influential where matter is sparse, voids are among the places where its large-scale effects may be especially noticeable. This does not mean dark energy is concentrated inside voids like gas in a container. In the simplest models, it is distributed uniformly throughout space. But inside a void, there is less matter to oppose the expansion associated with dark energy. The result is a region that can expand relatively quickly compared with dense structures. Astronomers study this behavior by measuring the sizes, shapes, and distribution of voids. If the properties of dark energy were different, the history of cosmic expansion would also be different. That would influence how quickly voids grew and how galaxies gathered around their edges. The modern pattern of voids, therefore, carries information about the past. It is like a frozen record of cosmic competition between gravity and expansion. One method used to study this pattern is called the void size function. Astronomers count how many voids exist at different sizes. Some cosmological models predict more small voids. Others predict larger or more rapidly expanding ones. By comparing observations with simulations, scientists can test which model best describes the universe. But identifying a void is not as simple as drawing a circle around an empty patch of sky. The universe is three-dimensional. Galaxies that appear close together in the sky may actually lie at very different distances. To map voids accurately, astronomers must measure the positions and redshifts of huge numbers of galaxies. Redshift is the stretching of light toward longer wavelengths. Part of this stretching is caused by the expansion of the universe. The farther away a galaxy is, the more its light is generally redshifted, although local motions also affect the measurement. Large galaxy surveys use these redshifts to create three-dimensional maps. In those maps, voids appear as broad regions with very few galaxies. Their boundaries are often irregular. Some are nearly round. Others are elongated, compressed, or connected to neighboring voids. Many are surrounded by walls and filaments rather than sharp edges. This complexity can reveal how gravity has acted around them. A small void inside a dense environment may eventually be squeezed by surrounding structures. A large void in an underdense region may continue expanding. Astronomers sometimes describe this as two different evolutionary paths. In one case, a void is crushed. In the other, it merges with neighboring underdense regions and grows. This behavior depends partly on the surrounding distribution of dark matter. Dark matter shapes voids even though voids contain less of it than average. At the center of a deep void, the dark matter density may be extremely low. Toward the edges, it rises, forming walls and filaments. Visible galaxies trace only part of this structure. A region may look empty because it contains few bright galaxies, yet still contain diffuse dark matter and faint dwarf systems. Simulations help estimate what lies between the visible traces. Scientists can begin with a map of galaxies and infer the likely dark matter distribution that produced it. They can also simulate universes with different kinds of dark matter. The standard model usually treats dark matter as cold and nearly collisionless. Cold means that its particles moved slowly enough in the early universe for small structures to form. Collisionless means that the particles rarely interact with one another except through gravity. This model successfully produces a web of filaments, halos, clusters, and voids similar to the observed universe. But it may not explain every detail on small scales. Alternative models can alter the structure of voids. Warm dark matter, for example, would erase some of the smallest early structures because its particles move more quickly. This could reduce the number of small halos and dwarf galaxies inside voids. Self-interacting dark matter could change how mass is distributed inside halos. Other theories modify gravity itself rather than introducing new dark matter properties. Void galaxies and void density profiles may help distinguish between these possibilities. A density profile describes how matter changes from the center of a void to its edge. A deep void may have an extremely underdense center, followed by a gradual rise in matter. Some voids also have a dense ridge around them, like a wall surrounding a basin. Different cosmological theories predict slightly different profiles. The challenge is that these differences can be subtle. Astronomers need very large surveys, accurate distances, and careful statistical analysis. They must also account for the fact that galaxies are biased tracers of matter. Not every dark matter halo contains a visible galaxy. Bright galaxies tend to form in more massive halos, while smaller halos may remain faint or dark. A map based only on bright galaxies can therefore make a void look emptier than it truly is. Dwarf galaxies are important because they provide additional tracers. The more faint systems astronomers can detect, the more detailed the void map becomes. Neutral hydrogen surveys add another layer. A small galaxy may be faint in visible light but rich in hydrogen. Radio telescopes can find these gas-bearing systems and reveal structures missed by optical surveys. Gravitational lensing offers yet another approach. A large concentration of matter bends light inward. A void, by contrast, contains less mass than average. Light passing through or near it may be bent slightly differently than light passing through a typical region. The effect is extremely weak, but when signals from many voids are combined, astronomers can search for a measurable pattern. This is called void lensing. Instead of observing one dramatic arc, scientists measure tiny statistical distortions in the shapes of many background galaxies. The signal can reveal the average mass distribution around voids. It can test whether the visible galaxies correctly trace the underlying dark matter. It can also help compare observations with cosmological models. Another valuable effect involves the cosmic microwave background. This ancient light has traveled across the universe since the cosmos was about 380,000 years old. As it passes through changing gravitational structures, its energy can be altered very slightly. A photon entering a gravitational well gains energy. When it climbs out, it normally loses the same amount. But if the gravitational structure changes while the photon is crossing it, the balance may not be perfect. In a universe with accelerated expansion, large voids and clusters can leave tiny temperature signatures in the cosmic microwave background. This phenomenon is related to the integrated Sachs-Wolfe effect. A photon passing through a large void may experience a gravitational landscape that becomes shallower during its journey. The resulting temperature change is extremely small. Scientists cannot usually detect it clearly for one void, so they combine observations of many voids and look for an average signal. The measurements are difficult and sometimes debated, but the possibility is extraordinary. Ancient light may carry a faint imprint from crossing a cosmic emptiness billions of years after it was released. Voids also affect how galaxies appear to move. Because matter tends to flow away from void centers and toward surrounding walls, galaxies near void boundaries can have coherent motions. These motions are called peculiar velocities. They are motions in addition to the general expansion of the universe. By measuring them, astronomers can study the gravitational forces around voids. A galaxy on the edge of a void may be moving outward relative to the void center. From another perspective, it is falling toward a denser filament. These are two descriptions of the same motion. The void loses matter while the cosmic web gains it. This flow can distort redshift maps. A spherical void in real space may appear stretched or compressed when mapped using redshifts because the galaxies have additional velocities. These redshift space distortions contain useful information. They reveal how quickly cosmic structure is growing. If gravity behaves differently from expectations, the flow of galaxies around voids may also differ. This makes voids useful for testing general relativity on enormous scales. Einstein's theory has passed many tests, from the motion of planets to the bending of starlight and the detection of gravitational waves. But scientists still ask whether gravity behaves exactly the same way across hundreds of millions of light-years. Some alternative theories attempt to explain cosmic acceleration without dark energy. They suggest that gravity itself may change at great distances or low densities. Voids are natural places to test these ideas because their gravitational environments are so weak. Certain modified gravity models predict that deviations from general relativity could be more visible inside voids than in dense regions. Dense objects can sometimes hide such effects through mechanisms that restore ordinary gravity. Low-density regions may offer less concealment. If galaxies, gas, or lensing signals around voids do not match the predictions of general relativity plus dark matter and dark energy, this could point toward new physics. So far, the standard cosmological model remains remarkably successful. It describes a universe containing ordinary matter, cold dark matter, and a cosmological constant associated with dark energy. This model is often abbreviated as lambda CDM. Lambda represents the cosmological constant. CDM stands for cold dark matter. Using only a small set of parameters, the model can reproduce many observed features of the universe, including the cosmic microwave background, the abundance of light elements, the distribution of galaxies, and the large-scale cosmic web. Yet important questions remain. What is dark matter made of? Why does dark energy exist? Is dark energy truly constant, or does it change over time? Why do the measured properties of the universe sometimes show tensions between different methods? Could gravity behave differently in the emptiest regions? Void studies may contribute to answering these questions. One particularly important tool is the Alcock-Paczynski test. The idea is based on geometry. If many cosmic voids have no preferred direction, their average shape should appear roughly spherical in real space. But converting observed angles and redshifts into physical distances requires assuming a cosmological model. If the assumed model is wrong, the average void may appear stretched along the line of sight or flattened across it. By finding the model that restores the expected average shape, astronomers can constrain cosmic expansion. This is a powerful approach because it uses the geometry of voids rather than relying only on their contents. However, peculiar velocities must be modeled carefully because they can also distort the shapes. Again, the apparently simple emptiness contains complex information. Void galaxies themselves add another clue. Their abundance, mass, gas content, and star formation histories depend on how small dark matter halos developed. If dark matter suppressed small-scale structure, fewer dwarf galaxies might form inside voids. If gravity was stronger or weaker in underdense regions, gas accretion and galaxy growth could change. By studying the faintest void galaxies, astronomers probe both cosmology and astrophysics. The two subjects are closely connected. Cosmology describes the universe as a whole. Astrophysics explains how individual galaxies, stars, and gas clouds behave. A cosmological model may predict how many halos form. Astrophysics determines which of those halos become visible galaxies. If observations disagree with predictions, scientists must determine where the problem lies. Perhaps the dark matter model is incomplete. Perhaps star formation is less efficient than expected. Perhaps radiation removed gas from small halos. Perhaps many faint galaxies have not yet been found. This uncertainty is not a weakness of science. It is the space where discovery happens. Every new telescope makes the map more complete. Wide optical surveys locate millions of galaxies. Radio observatories trace hydrogen. Space telescopes detect faint dwarf systems and distant background sources. Spectrographs measure redshifts and chemical compositions. Supercomputers simulate immense volumes of the universe. Each method reveals a different layer of the void. Some future surveys will map larger regions and detect fainter galaxies than ever before. They may discover entire populations of isolated dwarfs. They may measure void lensing with greater precision. They may test whether the expansion history matches a constant form of dark energy. They may reveal whether voids are shaped exactly as the standard model predicts. And perhaps they will uncover something unexpected. Science often advances when an observation refuses to fit a familiar pattern. A void may appear too empty. A dwarf galaxy may be found where no halo should have formed. A lensing signal may reveal more mass than visible traces suggest. A gas flow may move in a way that ordinary gravity cannot easily explain. One unusual result is not enough. But if many independent observations point in the same direction, our picture of the universe may change. Until then, cosmic voids remain quiet laboratories. They do not produce the brightest explosions. They do not contain the largest numbers of galaxies. They rarely dominate photographs of the night sky. Yet they may hold some of the purest evidence about the forces controlling cosmic history. There is something appropriate about that. The universe hides its deepest rules not only in brilliant objects, but also in the spaces between them. A cluster tells us how matter gathers. A void tells us what happens when matter leaves. Together, they complete the pattern. As you rest, imagine the cosmic web seen from an impossible distance. Bright filaments curve through space like softly glowing threads. Clusters shine at their intersections. Between them, enormous voids open like dark bubbles. The voids slowly expand. Galaxies near their edges drift toward denser walls. Ancient light passes through their interiors and emerges changed by an almost immeasurable amount. Dark matter shapes their boundaries. Dark energy influences their growth. And from these quiet spaces, astronomers try to read the hidden history of the universe. In the next part, we will look at the strange shapes and motions of void galaxies themselves, their warped disks, unusual rotations, faint companions, and the subtle signs that even the loneliest galaxies are never completely undisturbed. Warped disks, strange motions, and hidden companions. Here is a gentle cosmic mystery. Even a galaxy that appears completely alone may carry quiet evidence that something invisible has touched it. At first glance, void galaxies often seem peaceful. They are separated from the crowded environments of galaxy clusters. They experience fewer major collisions, fewer close encounters, and less gravitational disturbance from giant neighbors. Their isolation can allow them to preserve delicate disks of stars and gas for billions of years. But peaceful does not mean perfectly undisturbed. When astronomers examine void galaxies in greater detail, they often find subtle irregularities. A disk may bend upward on one side and downward on the other. Spiral arms may be uneven. Gas may rotate differently from the stars. A faint stream may extend into the darkness. Young stars may appear in places where no obvious trigger can be seen. These features suggest that isolation has many degrees. A galaxy may be far from every large neighbor while still interacting with a tiny dwarf companion, an incoming gas cloud, or a dark matter structure containing almost no stars. The outer regions of a galaxy are especially sensitive. Near the center, gravity is relatively strong. Billions of stars orbit within a deep gravitational field, and the structure can remain stable even when small disturbances occur. At the edge of the disk, matter is more loosely held. The gas is thinner, stars are more widely separated, and orbital periods are extremely long. A weak gravitational pull that would have little effect near the center can gradually reshape the outer disk. One common result is a galactic warp. A perfectly flat spiral galaxy would resemble a thin circular plate. But many real galaxies are not completely flat. Their outer edges curve away from the central plane, sometimes forming a shape similar to a softly bent sheet. The Milky Way itself has a warped outer disk. Void galaxies can display similar structures, even when no massive neighbor appears close enough to cause them. This creates an important question. What bends an isolated galaxy? One possibility is the slow arrival of intergalactic gas. Gas flowing toward a galaxy may not approach in the same plane as the existing disk. If it enters from a tilted direction, its angular momentum can pull the outer regions into a new orientation. Angular momentum describes the rotational motion of matter. A rotating galaxy possesses an enormous amount of it, accumulated during its formation and growth. Fresh gas brings its own rotational direction. If the two directions do not match, the galaxy may become warped. The inner disk remains relatively stable, while the more weakly bound outer gas tilts toward the incoming stream. Over time, new stars may form inside this tilted material. A warp can therefore become part of the visible stellar disk rather than remaining only in the gas. This means the shape of a galaxy may preserve the direction from which matter once arrived. Another possible cause is a faint companion. A small dwarf galaxy can be extremely difficult to detect, particularly if it contains few stars and has a low surface brightness. Yet its gravity can still influence a larger system. During a close passage, the dwarf may pull on one side of the disk. It can create a warp, stretch a spiral arm, or disturb the distribution of hydrogen. The companion itself may later move away, merge with the galaxy, or become too faint to identify. The evidence remains after the visitor is gone. Astronomers sometimes find isolated galaxies with unusually asymmetric shapes. One side may extend farther than the other. A spiral arm may appear strong and bright on one side but weak on the opposite side. The center of the stellar disk may not align perfectly with the center of the gas. This unevenness is known as lopsidedness. Lopsided galaxies are common enough that they cannot all be explained by dramatic recent collisions. In void environments, the cause may be long-lasting internal oscillations, uneven gas accretion, or interactions with tiny companions. A disturbance can persist for many galactic rotations. Since a single rotation may take hundreds of millions of years, the visible irregularity could be a record of an event that happened far in the past. The galaxy remembers through motion. Gas is particularly useful for reading this memory. Stars usually move in relatively regular orbits, but interstellar gas can be compressed, heated, cooled, and displaced. Radio observations of neutral hydrogen often reveal structures extending far beyond the visible stellar disk. A galaxy that looks symmetrical in ordinary light may appear dramatically irregular in hydrogen. Its gas may form a long tail. It may gather into a cloud on one side. It may stretch into a bridge leading toward a faint companion. It may rotate in a tilted ring around the main body of the galaxy. These features provide clues about past accretion and interaction. Sometimes the gas rotates in the opposite direction from the stars. This is known as counter-rotation. Imagine most of the stars in a galaxy orbiting clockwise while part of the gas moves counterclockwise. Such a configuration is difficult to produce if all the material formed together from a single rotating cloud. Counter-rotating gas probably arrived later. The galaxy may have captured it from outside, perhaps from a small companion or an intergalactic stream with a different orientation. If the captured gas becomes dense enough, it can form new stars that inherit its direction of motion. A galaxy may then contain two stellar populations rotating against one another. This sounds chaotic, but the structures can remain stable for long periods under the right conditions. The stars rarely collide directly because the distances between them are immense. Two opposing stellar disks can pass through each other again and again while gravity shapes their collective motion. The gas behaves differently. Gas clouds can collide, creating shocks and losing energy. Counter-rotating gas may therefore move inward more efficiently, feeding central star formation or a black hole. Even a subtle external event can change the future of the entire galaxy. Polar rings provide an even more dramatic example. In a polar ring galaxy, a ring of gas and stars orbits nearly perpendicular to the main galactic disk. The central galaxy may appear as one flat system, while a second luminous structure circles around it from a completely different angle. Such rings are usually associated with captured material or ancient interactions. A galaxy may pull gas from a passing companion and arrange it into a stable polar orbit. Because the ring travels through the galaxy's dark matter halo in an unusual direction, its motion can help astronomers study the halo's shape. If the dark matter distribution is nearly spherical, the ring may remain stable. If the halo is strongly flattened or irregular, the orbit can change in measurable ways. A strange galactic feature becomes a tool for mapping invisible matter. Polar ring systems are rare, and identifying one inside a void is especially interesting. Its existence may reveal that small-scale interactions continue even where large galaxies are scarce. Another unusual structure is a ring galaxy. Some ring galaxies form after one galaxy passes nearly through the center of another. The collision sends a wave outward through the disk, compressing gas and triggering star formation in a circular pattern. The result can resemble a bright blue ring surrounding a quieter center. This kind of direct collision is unlikely in the emptiest regions, but voids are vast and ancient. Rare events still have billions of years in which to occur. A galaxy now considered isolated may have interacted with another system long ago. Its former companion may have merged with it or moved far away. Current surroundings do not always reveal past surroundings. Galaxies travel. Voids expand. Small groups can separate. To understand a galaxy, astronomers must reconstruct not only where it is now, but also where it may have been. Computer simulations are essential for this work. Researchers can create models of galaxies with stars, gas, and dark matter. They introduce a passing dwarf, an incoming gas stream, or a tilted halo and observe the resulting structure. Does the simulated disk develop the same warp? Does the hydrogen form a similar tail? How long does the asymmetry survive? By comparing simulations with observations, scientists identify the most likely history. Still, more than one explanation can sometimes produce a similar result. A warp caused by gas accretion may resemble a warp caused by a companion. A lopsided disk may result from internal instability or an external encounter. Astronomy often involves choosing between several stories written in the same faint evidence. The motion of the galaxy can help. Astronomers measure velocity using the Doppler effect. Light shifts slightly toward longer wavelengths when an object moves away and toward shorter wavelengths when it approaches. By measuring this shift across different parts of a galaxy, scientists create a velocity map. One side of a rotating disk generally approaches us while the other moves away. If the rotation is smooth, the velocity pattern appears orderly. If gas clouds are moving inward, outward, or at tilted angles, the map becomes more complex. A disturbed galaxy may show bends, twists, or sudden changes in its velocity field. These motions can reveal structures that are difficult to see directly. Suppose a galaxy contains a dark companion with almost no stars. Its gravity may pull on the visible disk, causing a local change in rotation. Astronomers may notice that the stars or gas move faster in one region than expected. The companion itself remains invisible, but its influence appears in the velocity map. This is similar to discovering a planet by observing the slight movement of its star. Gravity reveals what light conceals. Rotation curves provide one of the most important examples. If most of a galaxy's mass were concentrated in its visible center, orbital speeds should decline with distance. Instead, the outer gas of many galaxies continues rotating rapidly. This is strong evidence for extended dark matter halos. Void galaxies allow astronomers to ask whether those halos differ from halos in crowded environments. Do isolated galaxies have more regular dark matter distributions? Are their halos rounder because they have experienced fewer mergers? Do small void galaxies rotate in the way cold dark matter models predict? The answers are difficult because dwarf galaxies often rotate slowly, and their gas is affected by turbulence. Random motion can be comparable to organized rotation. Astronomers must separate the two carefully. The angle at which the disk is viewed also matters. A nearly face-on galaxy may show little line-of-sight motion even if it rotates rapidly. A small error in the estimated angle can greatly affect the calculated speed. For this reason, precise images and velocity measurements must be combined. Some void dwarf galaxies appear to rotate very slowly despite containing large amounts of gas. This has led to interest in objects that may be unusually deficient in dark matter, although such claims require caution. A galaxy could appear to contain little dark matter if its distance, orientation, or internal motion has been misunderstood. If true dark matter-poor galaxies exist, they may have formed through unusual processes, perhaps from material stripped during interactions. But such an origin is harder to explain in deep cosmic voids. An isolated dark matter-poor galaxy would challenge simple ideas about galaxy formation, since galaxies are generally expected to grow inside dark matter halos. Again, the quietest environments can produce the loudest scientific questions. Bars are another important feature. A galactic bar is an elongated structure of stars extending through the center of some disk galaxies. The Milky Way has one. Bars rotate and influence the orbits of stars and gas. They can guide gas toward the central regions, where it may form stars or feed a black hole. A galaxy does not need an external collision to form a bar. The structure can arise from an internal instability in the disk. This makes barred void galaxies useful for understanding how galaxies evolve through their own dynamics. In a crowded environment, it can be difficult to know whether a bar was created or strengthened by an encounter. In a deeply isolated galaxy, internal evolution becomes a more likely explanation. The bar gradually rearranges the galaxy. It can move angular momentum outward. Gas flows inward along its edges. Rings may form near regions where orbital patterns interact. Over billions of years, the central part of the galaxy may become denser and rounder. This slow internal transformation is known as secular evolution. The word secular here means occurring gradually over long periods rather than through sudden dramatic events. Void galaxies may be ideal places to observe secular evolution. Without frequent mergers, internal structures have time to shape the system gently. A spiral arm can redistribute material. A bar can feed the center. A warp can slowly settle. A cloud can move inward and trigger a small burst of star formation. The galaxy changes without losing its identity. Spiral structure itself remains partly mysterious. Some spiral arms may behave like long-lived density waves. Others may be temporary patterns that repeatedly form and fade. Interactions can create or strengthen them, but isolated disks can also generate spirals through internal gravitational processes. Void spirals therefore help astronomers test whether beautiful galactic patterns require external companions. In many cases, they do not. A rotating disk of stars and gas can organize itself into arms because small disturbances are amplified by gravity and differential rotation. Differential rotation means that material at different distances from the center completes its orbit in different amounts of time. The inner parts usually orbit more quickly than the outer parts. This motion stretches features into curved patterns. Gas enters the denser regions of an arm, becomes compressed, and may form stars. The young stars illuminate the arm, making it appear like a permanent structure even if the pattern itself changes. A galaxy can create its own beauty through motion. Magnetic fields may also influence its gas. Galactic magnetic fields are weak compared with everyday magnets, but they extend across enormous distances. They can guide charged particles, affect turbulence, and shape regions of star formation. The origin and maintenance of these fields are active areas of research. Rotating gas and turbulent motion may strengthen them through a process known as a dynamo. In an isolated galaxy, the magnetic field develops without repeated disruption from cluster environments. Radio polarization observations can reveal its structure. Fields may follow spiral arms, stretch along bars, or bend through warped disks. The galaxy possesses an invisible architecture layered over its dark matter halo and visible stars. Cosmic rays add another hidden component. These are high-energy particles produced by supernovae, black holes, and other energetic sources. Magnetic fields scatter them through a galaxy. As cosmic rays travel, they can heat and ionize gas. They may contribute pressure that helps drive material outward. In dwarf galaxies with weak gravity, this pressure can influence whether gas escapes or remains available for future star formation. A void galaxy may therefore be shaped by processes too small to see directly but powerful when acting across millions of years. A supernova releases cosmic rays. Magnetic fields guide them. Gas is pushed toward the halo. Some of it cools and returns. The cycle continues. Interactions with the cosmic web may also affect the direction in which galaxies spin. Computer simulations suggest that the orientation of a galaxy can be connected to the filament in which it formed. Small galaxies may align differently from massive ones because their growth histories are different. Inside voids, where filaments are thin, these alignments may offer clues to the hidden structure. Astronomers can compare the directions of galaxy disks with the shapes of nearby void boundaries or faint galaxy chains. If a pattern appears across many systems, it may show how angular momentum was acquired in the early universe. A galaxy's rotation may preserve a memory of forces acting billions of years ago. This is one of the most remarkable ideas in cosmic structure. The direction in which stars orbit today may be connected to tiny gravitational imbalances present before the first galaxies existed. Every spin has a history. Void galaxies also move together in larger flows. They are carried by the expansion of the universe, but they also respond to the gravity of distant filaments, walls, and clusters. A galaxy near the center of a void may move outward toward the boundary. A galaxy near the edge may join a stream flowing along a filament. These motions are slow compared with light, but they shape the cosmic web over time. The void becomes emptier. The boundary becomes denser. Galaxies that began far apart may eventually join the same wall. Even isolation can be temporary on cosmological timescales. Yet some deep void galaxies may remain separated from large structures for the foreseeable future. As cosmic expansion accelerates, extremely distant regions become harder to reach and eventually harder to observe. A lonely galaxy may become more isolated with time. Its local companions, however, can remain gravitationally bound. A pair of dwarf galaxies inside a void may slowly approach one another and merge, even while the larger universe expands around them. Their private interaction unfolds within an increasingly empty horizon. The merger may create a larger irregular galaxy, compress gas, and produce a burst of blue stars. For a brief period, one of the quietest regions of the universe can contain a brilliant event. Then the new galaxy settles. The brightest massive stars die. Gas cools. The void becomes calm again. This cycle reminds us that cosmic silence is not the absence of change. It is change occurring on scales too slow and vast for human senses. A warp may take 1 billion years to develop. A companion may complete a single orbit in several billion years. A gas stream may travel across a galactic halo for longer than complex life has existed on Earth. Nothing appears hurried. So, as you rest, imagine a pale spiral galaxy floating deep inside a void. Its central disk turns smoothly, but the outer hydrogen bends upward like the edge of a gentle wave. On one side, a faint arm stretches toward a tiny companion that is almost lost in the darkness. A stream of fresh gas approaches from above the disk. Its motion is slightly different from the motion of the stars. Far inside the galaxy, a bar slowly guides gas toward the center. Along the outer warp, several blue stars have recently begun to shine. The galaxy is not being torn apart. It is simply responding to quiet influences: gravity, motion, invisible matter, and the distant flow of the cosmic web. Its unusual shape is a history written without words. And in the next part, we will explore what it might be like to look outward from a world inside a void galaxy, beneath one of the darkest and most isolated skies imaginable. The night sky inside a void galaxy. Imagine standing on a quiet world beneath a night sky so dark that the universe itself seems to have stepped far away. A planet inside a void galaxy could orbit an ordinary star. It might have mountains, oceans, clouds, and seasons. Its inhabitants, if any existed, could watch moons rise, follow the paths of planets, and see the pale glow of their own galaxy stretching across the sky. But beyond that local light, the heavens might appear unusually empty. From Earth, astronomers can observe many neighboring galaxies. The Andromeda Galaxy is visible to the unaided eye under dark conditions, and powerful telescopes reveal countless more. Some are spirals, some are elliptical, and others are irregular clouds of stars. Inside a deep cosmic void, the nearest large galaxy might be millions or even tens of millions of light-years away. To an observer without advanced instruments, it could be completely invisible. Their night sky would still contain stars because they would live inside a galaxy of their own. Bright nearby suns would form constellations. Star clusters and nebulae might glow beautifully. A band of galactic light could arch overhead, just as the Milky Way does in Earth's sky. Yet the space beyond the galaxy might seem almost completely black. This could deeply influence the way such a civilization understood the universe. Early astronomers on Earth once believed that the Milky Way might contain nearly everything that existed. Only during the 20th century was it firmly established that many faint objects in the sky were separate galaxies located far beyond our own. For observers inside an isolated void galaxy, that discovery might come much later. Their nearest galactic neighbors would be fainter and more difficult to detect. Even large telescopes might initially reveal only a few dim smudges in the distance. The inhabitants could spend centuries believing that their galaxy was alone. They might develop mathematics, physics, and astronomy while possessing no clear evidence of galaxy clusters or the enormous cosmic web. Their first deep image of another galaxy could become one of the most important moments in their history. A tiny patch of light would show that the darkness beyond their stars was not truly empty. With more powerful telescopes, additional galaxies would slowly appear. The farther astronomers looked, the farther back in time they would see, because light takes time to travel. Eventually, they might discover something strange. Although their nearby universe looked almost vacant, the distant universe would contain far more galaxies. This would reveal that their home occupied an unusual region. They would realize that they lived inside a cosmic void, a vast underdense space surrounded by distant walls and filaments of galaxies. Their apparent loneliness would become evidence of the universe's large-scale structure. Measuring this structure would not be easy. A galaxy is not a small point with a simple distance label. Astronomers must study its light, estimate its redshift, and determine how fast cosmic expansion has stretched the wavelengths. Thousands or millions of such measurements are needed to create a three-dimensional map. From inside a void, the first maps might show a great empty region centered roughly around the observers themselves. At first, this could seem suspicious. Throughout history, humans have often imagined themselves at the center of the cosmos. A civilization in a void might make the same mistake, believing that the emptiness around its galaxy meant it occupied a special central position. But careful observation would reveal otherwise. The void would have a shape and boundary. Its home galaxy might not lie exactly at the center. Beyond the emptiness, galaxies would gather into filaments, clusters, and walls. The universe would not be arranged around the observers. They would simply live in an uncommon neighborhood. Their view of cosmic history might also differ from ours. Astronomers on Earth study nearby galaxies to understand star formation, black holes, dark matter, and galactic collisions. A civilization in a deep void would have fewer nearby examples. It might be difficult for them to observe major galaxy mergers in detail. Rich clusters would be very distant. Gravitational lensing by massive structures might require extremely sensitive instruments. On the other hand, their isolated location could offer advantages. Their sky might contain less interference from nearby bright galaxies. The space around them could provide a clean view of very distant objects. With sufficiently advanced technology, they might study the early universe through an unusually quiet foreground. Their own galaxy could also serve as an ideal laboratory for isolated evolution. They might learn how stars form without frequent external disturbances. They could map enormous hydrogen clouds, faint dwarf companions, and the dark matter halo surrounding their home. They might discover that their galaxy was not as alone as it first appeared. Tiny satellite galaxies could orbit far beyond the main stellar disk. Dark gas clouds might move through the halo. Thin streams of matter could connect the galaxy to faint structures crossing the void. The loneliness would contain hidden complexity. The constellations on such a world would depend on its location within the galaxy. Near the galactic center, the sky could be crowded with stars. Some might appear extremely bright because the average distance between neighboring systems would be smaller. Near the outer edge, the sky could look darker and more open. One side might face the glowing center of the galaxy, while the other faced the vast cosmic void. The contrast could be extraordinary. In one direction, billions of stars would blend into a soft band of light. In the opposite direction, only a few faint stars would interrupt the darkness, and almost no external galaxies would be visible without powerful telescopes. A world there would have a front-row view of cosmic emptiness. Its inhabitants might build observatories on the side of their planet that faced away from the galactic center. The night would be exceptionally dark, allowing them to detect weak signals from deep space. They could search for distant supernovae, quasars, and the faint afterglow of the Big Bang. The cosmic microwave background would surround them just as it surrounds us. It is present in every direction, a nearly uniform field of ancient radiation left from the early universe. Living inside a void would not place them outside this cosmic history. They would still see evidence that the universe began in a hot, dense state. They would still observe expansion. They would still find the same chemical elements, physical laws, and fundamental particles. Their neighborhood would be unusual, but the universe would remain connected. This is an important truth about cosmic isolation. A void galaxy may seem separated from everything else, yet it shares the same origin as every cluster and filament. Its hydrogen formed in the early universe. Its heavier elements were created inside stars. Its dark matter halo grew from ancient density fluctuations. Its light travels outward and eventually joins the light of the wider cosmos. Even the loneliest galaxy is part of the same story. Perhaps a civilization there would find comfort in this discovery. For generations, it might believe that its island of stars was surrounded by endless emptiness. Then, gradually, astronomy would reveal distant communities of galaxies arranged across unimaginable scales. They would learn that they were isolated, but not alone. Their telescopes would become bridges across the void. Every photon collected from a distant galaxy would have traveled for millions or billions of years before reaching them. Some of those photons would have begun their journey before their planet existed. A detector no larger than a room could capture light that had crossed an enormous cosmic desert. Through that light, the inhabitants could study stars they would never reach and galaxies they could never visit. Astronomy would turn distance into knowledge. And perhaps, as they looked into the deep darkness, they would wonder whether another civilization was also looking back from a distant filament. The separation would be almost impossible to cross. Even a message traveling at the speed of light could require millions of years to arrive. But the possibility would still exist. Somewhere beyond the void, another observer might see their galaxy as a faint point inside an apparently empty region. Each would know the other only through ancient light. There is something peaceful in this image. Two distant worlds do not need to meet to share the same universe. Their stars are governed by the same gravity. Their atoms follow the same physical laws. Their skies contain light from the same cosmic beginning. Distance separates them, but history connects them. So, as you relax, imagine standing beneath the sky of a world near the edge of a void galaxy. Behind you, the galaxy glows like a soft river of stars. Ahead, darkness stretches across millions of light years. At first, it seems empty. Then a telescope turns toward that darkness. A faint spiral appears. Another point of light follows. Slowly, the hidden universe reveals itself. And in the next part, we will travel into the future of void galaxies to discover what may happen as cosmic expansion continues and the universe grows darker, colder, and increasingly isolated. The distant future of void galaxies. Here is a quiet thought for the night. the loneliest galaxies in the universe may become even lonelier as time continues. Today, cosmic voids are already enormous. Their galaxies are separated by distances so vast that light may travel for millions of years between neighboring systems. But the universe is still expanding, and that expansion is accelerating. Over immense periods of time, the spaces between distant, unbound galaxies will continue to grow. A void galaxy will not simply remain where it is while empty space stretches around it. Its entire cosmic neighborhood will evolve. Nearby dwarf companions may merge with it, gas may continue to fall inward, and stars will keep forming for as long as enough cold material remains. But beyond its local gravitational family, the wider universe will slowly recede. This future is sometimes described as the era of increasing cosmic isolation. Gravity can hold nearby structures together. The stars of a galaxy remain bound to one another. A small group of neighboring galaxies may eventually merge into a single larger system. But galaxies separated by sufficiently large distances are carried apart by the expansion of space. For a galaxy deep inside a void, the nearest large structures may move farther away until their light becomes increasingly faint and redshifted. Redshift means that the wavelength of light is stretched. As space expands during a photon's journey, visible light can shift toward infrared wavelengths, then toward microwaves, and eventually into frequencies that are extremely difficult to detect. A distant galaxy does not suddenly disappear. Its light becomes dimmer, redder, and older. Over trillions of years, many galaxies that are visible today may move beyond what future observers can practically see. Their ancient light will fade below the limits of any ordinary telescope. A civilization born in the far future of a void galaxy could therefore face an even darker sky than the one imagined in the previous part. It might see only its own merged galactic system. The cosmic web could be hidden from view. Galaxy clusters beyond the local gravitational region might no longer appear as faint points. The evidence of the broader universe could become extremely difficult to recover. Future astronomers might look outward and conclude that their galaxy was surrounded by endless, empty space. The great expansion of the universe would have erased much of the observable evidence of its own history. This is one of the strangest predictions of modern cosmology. Knowledge that is available now may not remain equally accessible forever. We live during an era when distant galaxies are still visible, the cosmic microwave background can still be measured, and the large-scale cosmic web can be mapped. The universe has given us a temporary window into its past. Inside a void galaxy, this window may close earlier in a practical sense because nearby bright structures are already scarce. The stars within the galaxy, however, will continue their own much slower story. Star formation does not end immediately. A gas-rich void galaxy may retain hydrogen for billions or even tens of billions of years. It may continue producing new stars at a gentle rate long after more active galaxies have consumed much of their fuel. Isolation can help preserve this gas. There are fewer collisions to trigger enormous starbursts that rapidly use it. There is no dense cluster environment to strip it away. A small galaxy may burn through its resources like a candle with a very low flame. But eventually, the available cold gas will decline. Some will be locked inside long-lived stars and planets. Some will be heated by supernovae and stellar radiation. Some may escape the weak gravity of a dwarf galaxy. Some may remain too diffused to collapse again. As the supply falls, new star formation will become rarer. The brightest blue stars will disappear first because their lives are brief. Massive stars consume their fuel quickly and end as supernovae or black holes. Without new generations replacing them, the galaxy's color will slowly change. It will become redder and dimmer. Sun-like stars will continue shining for billions of years. Smaller red dwarf stars may last much longer. Red dwarfs are the quiet survivors of the stellar population. They are smaller, cooler, and fainter than the Sun, but they use their fuel very efficiently. The least massive ones may shine for trillions of years. No red dwarf has yet reached the end of its natural life, because the universe is not old enough. In the distant future, these stars may become the primary sources of visible light. A once blue void galaxy filled with young star-forming regions could become a faint reddish island. Its night sky would still contain stars, but fewer brilliant ones. The longest-lived stars would glow gently while the darkness around them deepened. Planets could continue orbiting these red dwarfs for extraordinary lengths of time. Some might remain warm if they orbit close enough. Others could become frozen as their stars slowly change. The possibility of life around red dwarfs is complex. These stars can produce powerful flares, especially when young. Planets close to them may become tidally locked, with one side facing the star. Yet their long lifetimes provide enormous spans of time during which stable conditions might develop. If life can adapt to such environments, void galaxies could remain inhabited long after bright stars become rare. The future of a planet also depends on the evolution of its star. A star similar to the Sun eventually expands into a red giant. It sheds its outer layers, leaving behind a dense white dwarf. A white dwarf is roughly the size of Earth but contains a mass comparable to that of the Sun. At first, it is very hot. It no longer produces energy through ordinary nuclear fusion. Instead, it slowly radiates stored heat into space. Over unimaginable periods, it cools and fades. The universe is not old enough for any white dwarf to have cooled completely. Hypothetical fully cooled remnants are sometimes called black dwarfs. They do not exist yet. If they eventually form, the universe will have entered an age far beyond the current stellar era. Void galaxies will then contain enormous populations of dark stellar remnants. White dwarfs, neutron stars, black holes, cold planets, asteroids, brown dwarfs that were never massive enough to ignite sustained hydrogen fusion. The bright galaxy will become a dark gravitational structure filled with fading objects. Before that happens, galaxies may undergo internal transformations. If a void galaxy has companions, gravity may slowly draw them together. Two dwarf galaxies can orbit for billions of years before merging. Their gas may collide and create one final burst of star formation. The merger can reshape both systems into a larger, smoother galaxy. A small group may eventually become one isolated stellar island. This process is expected to occur in many gravitationally bound galaxy groups, including our own local group. The Milky Way and Andromeda are moving toward one another and are expected to interact in the distant future, although the exact sequence remains uncertain. Void systems are often smaller, but the same gravitational principle applies. Expansion does not pull apart objects that are tightly bound. Within a galaxy, gravity easily overcomes cosmic expansion. Stars do not drift away from one another merely because the universe expands. Planets remain in orbit. Galaxies remain intact. Only on much larger scales does expansion dominate. This distinction is important. The future universe will not become a uniform mist of stars. Instead, matter will remain concentrated into isolated gravitational islands, while the distances between those islands become enormous. A void galaxy may merge with everything close enough to be bound and then spend the rest of cosmic history almost completely alone. Its future astronomers might find ancient records describing galaxies that are no longer visible. They may possess old images of the cosmic web and wonder whether those distant lights truly existed. The scientific evidence could still survive locally. The chemical composition of stars would reveal earlier generations. The motion of the galaxy could reveal dark matter. The abundance of hydrogen and helium could provide clues about the early universe. But some major cosmological observations would be missing. The cosmic microwave background would continue to cool and redshift. Today, its temperature is only a few degrees above absolute zero. As the universe expands, its wavelengths stretch and its temperature decreases. In the far future, the signal may become so weak and long wavelength that it is hidden by other effects or impossible to measure from within a galaxy. Without this ancient radiation, future scientists would lose one of the strongest pieces of evidence for the hot early universe. Cosmic expansion itself might also become difficult to detect. If all visible galaxies were gravitationally bound into one local system, there would be no distant objects available to show the Hubble flow. Astronomers might observe local motions but see no clear sign that space on the largest scales was expanding. The universe could appear static, dark, and eternal. They might have to reconstruct its true history from ancient archives or subtle physical clues. This gives our present era a special significance. We are able to observe the universe while it is still filled with visible evidence of its evolution. We see galaxies at many stages of development. We detect light that has traveled for more than 13 billion years. We map voids, filaments, and clusters. We can look outward from one galaxy and discover the architecture of the entire observable cosmos. Void galaxies make this privilege especially clear. Their isolation gives us a preview of the far future. They show what a galaxy looks like when the lights of its neighbors are already distant. As expansion continues, more galaxies will resemble them. The universe will become less like a crowded web of visible lights and more like a collection of separate islands, each surrounded by a growing ocean of inaccessible space. Black holes will also become increasingly important. Small black holes formed by dying stars can persist for extraordinary spans of time. Supermassive black holes may sit at the centers of merged galaxies. Once stars and gas become scarce, these black holes may receive little new material. They will enter long periods of darkness. According to quantum theory, black holes may slowly lose mass through Hawking radiation. For a stellar mass black hole, this process would take an almost inconceivably long time. For a supermassive black hole, it would take vastly longer. The numbers exceed ordinary intuition. 1 trillion years, already far longer than the current age of the universe, would represent only an early chapter. The black hole era could continue for times written with dozens of zeros. Eventually, if current theories are correct, even black holes would evaporate. The universe would then contain mostly low-energy particles, radiation, and perhaps dark matter, depending on its true nature and stability. This possible future is often called heat death. The name sounds dramatic, but the process is quiet. Energy becomes increasingly spread out. Fewer differences remain that can be used to perform work. There are no bright stars, no warm planets, and no large supplies of cold gas collapsing into new objects. The universe approaches a state of maximum entropy. Yet this future lies so far away that even language struggles to describe the time involved. The void galaxies we observe today are still young by comparison. They contain shining stars. They hold gas. Some are creating planets at this very moment. Their future darkness should not make their present light feel less meaningful. In fact, it makes every star-forming cloud more remarkable. A small blue star in a void galaxy is a temporary victory over cosmic darkness. For a few million years, it shines with tremendous power. Its light crosses the empty region and travels toward distant filaments. Long after the star has exploded, some of those photons may still be moving through intergalactic space. Light continues after its source is gone. Some photons emitted by void galaxies today will travel through the expanding universe for billions of years without being absorbed. Their wavelengths will stretch. Their energy will decrease. But they will preserve a faint memory of the galaxy that created them. The future of dark energy remains uncertain. In the simplest model, the accelerating expansion continues indefinitely at a steady rate associated with a cosmological constant. But scientists also consider other possibilities. Dark energy might change over time. It could weaken. It could strengthen. Its true nature is unknown. If it became much stronger, expansion could eventually affect smaller structures in a hypothetical scenario known as the Big Rip. Galaxies, stars, planets, and even atoms could be pulled apart. This idea is not the standard expectation and depends on a particular form of dark energy for which there is no firm evidence. Another possibility is that cosmic acceleration could eventually stop or reverse, although current observations do not indicate an approaching collapse. Because dark energy remains mysterious, the very distant future cannot be described with complete certainty. Void observations may help reduce that uncertainty. Since voids are sensitive to cosmic expansion, their sizes and motions can constrain how dark energy behaves. By studying emptiness today, astronomers are trying to understand the fate of everything. There is something beautifully circular in that. The smallest fluctuations in the early universe created voids. Voids now help us measure expansion. Expansion will make future galaxies increasingly isolated. Those isolated galaxies may eventually lose sight of the wider universe that created them. The story begins and ends with darkness, but between those periods lies an age of stars. We live within that luminous age now. So, as you rest, imagine a void galaxy billions of years in the future. Its blue star-forming clouds have faded. Its remaining stars glow softly in shades of orange and red. A few small companions have merged into its outer halo. Beyond them, the universe appears almost completely black. The distant cosmic web has passed beyond sight. A red dwarf illuminates a small planet, and from that planet, an observer looks upward. The observer sees fewer stars than we do, but each one carries an ancient history. They may not know how crowded the universe once appeared, but somewhere in their archives is an image of countless galaxies arranged along shining filaments. A message from the universe's youth. A reminder that their quiet island was once part of a visible cosmic ocean. And in the final part, we will bring our journey together by exploring the deepest mysteries still hidden inside voids. Undiscovered galaxies, unexplained motions, ancient gas, and the questions that future telescopes may finally answer. The final mysteries hidden in cosmic voids. Here is one last peaceful thought. The darkest places in the universe may still be filled with discoveries waiting quietly for someone to notice them. We have traveled through the enormous cosmic voids that separate the bright filaments of the universe. We have visited isolated galaxies, followed invisible gas streams, explored dark matter halos, and imagined stars being born in places where almost nothing seems to exist. Yet much about these regions remains unknown. Cosmic voids are difficult to study because they are defined by absence. Astronomers usually learn about the universe by collecting light, but voids contain fewer bright sources. Their dwarf galaxies can be extremely faint. Their gas is thin. Their dark matter cannot be observed directly. To understand them, scientists must search for very small signals across enormous distances. A dim galaxy may appear as only a soft patch of light. A hydrogen cloud may be detected as a weak radio signal. A dark matter filament may reveal itself only through the movement of nearby galaxies or a slight distortion in background light. Every discovery requires patience. One of the greatest unanswered questions is how many galaxies are still hidden inside voids. Current maps are built mostly from galaxies bright enough to detect. But a void that appears nearly empty may contain many ultra-faint dwarf galaxies below the limits of existing surveys. Some may have only a few thousand visible stars. Others may be extremely diffuse, spreading their light across such a large area that they blend into the background sky. A galaxy can contain millions of stars and still remain difficult to see if those stars are widely separated. Future telescopes may reveal entire hidden populations. As surveys become deeper and more sensitive, astronomers will search for low surface brightness galaxies, gas-rich dwarfs, and systems that have formed stars only occasionally. Each newly discovered galaxy will change the map. A large void may become a network of smaller empty regions separated by delicate chains of dwarfs. What once looked like a single dark bubble may reveal an internal structure resembling a miniature cosmic web. This would not make the void disappear. The region would still contain far less matter than average, but its emptiness would become more detailed. Another mystery concerns galaxies that appear unusually young. Some void dwarfs contain very few heavy elements and large amounts of pristine-looking gas. Their bright blue stars suggest recent activity, while their faint older stars can be difficult to detect. Could any nearby galaxy truly be forming its first significant generation of stars? Most astronomers expect that nearly all known galaxies contain at least some ancient stars. Even systems that look young probably began forming stars billions of years ago. But an extremely isolated dark matter halo may have delayed most of its star formation. Fresh gas could enter late. A small interaction might finally compress the material. After spending much of cosmic history in darkness, the system could begin shining more strongly in the modern universe. Finding such a galaxy would be remarkable. It would offer a rare view of star formation under conditions that resemble an earlier cosmic age. Deep observations of individual stars can help solve this mystery. When a galaxy is close enough, a powerful telescope can separate its light into individual points. Astronomers can then compare the brightness and colors of its stars. Older stars occupy different patterns from younger ones. A population of faint red giants would reveal that the galaxy has existed and formed stars for a long time, even if its current appearance is dominated by bright blue clusters. The oldest stars are often the quietest witnesses. They may be difficult to see, but they carry the beginning of the galaxy's history. The origin of gas inside void galaxies is another open question. Some gas may have remained from the galaxy's early formation. Some may have been recycled through generations of stars. Some may arrive from the surrounding cosmic web. Astronomers want to know how much fresh material continues to enter galaxies today. Incoming gas is usually faint and difficult to observe directly. It may be warm, ionized, and spread across a large volume. Only after it cools and gathers near the galaxy does it become easier to detect. Chemical composition provides clues. Gas that has spent time inside stars becomes enriched with heavy elements. Fresh intergalactic gas should generally contain fewer of them. If a galaxy contains a region with unusually low metallicity, this may indicate recent accretion. But gas can mix. Stellar explosions can spread metals unevenly. A low metallicity region could also result from an unusual internal history. Scientists therefore combine chemical measurements with maps of gas motion and star formation. A stream moving toward the disk, a warped hydrogen layer, and a chemically primitive star-forming region together create a stronger case for fresh accretion. Future radio telescopes will map neutral hydrogen with much greater detail. They may detect thin bridges connecting void galaxies, extended gas disks, and small clouds without visible stars. Some of these clouds could reveal the hidden filaments supplying isolated systems. Others might be nearly dark galaxies. The difference may depend on whether the gas is rotating inside its own dark matter halo or simply drifting through space. The nature of dark matter remains perhaps the largest mystery. Void galaxies are small, isolated, and often strongly dominated by dark matter. This makes them promising places to test how invisible mass is distributed. But measuring it precisely is difficult. Astronomers infer mass from motion. They observe how stars and gas orbit the center. Faster motion usually indicates stronger gravity and therefore more mass. In dwarf galaxies, however, the motions can be messy. Gas is stirred by supernovae. Stars may move randomly rather than in a thin rotating disk. The galaxy may be tilted at an uncertain angle. Its distance may not be known perfectly. Small measurement errors can produce large differences in the estimated dark matter content. Researchers need detailed observations of many galaxies, not just a few unusual examples. Patterns across an entire population are more reliable than one surprising object. If void dwarfs consistently show fewer small halos than expected, this might challenge cold dark matter models. If hidden galaxies are eventually found in the predicted numbers, the standard model would become stronger. Either result would teach us something important. Voids may also test whether gravity behaves differently in low-density environments. General relativity describes gravity with extraordinary success, but it has not been tested equally at every scale and density. Some alternative theories predict small changes that are hidden in massive systems but become more noticeable in voids. Astronomers can study the motions of galaxies around void boundaries, the bending of background light, and the rate at which structures grow. If these measurements differ from standard predictions, the cause could be new gravitational physics. But the interpretation must be cautious. Ordinary astrophysical processes can imitate unexpected signals. Incomplete galaxy surveys can distort void maps. Incorrect assumptions about galaxy distances can change their apparent shapes. Extraordinary conclusions require many independent lines of evidence. Dark energy introduces an even deeper uncertainty. The accelerated expansion of the universe is well supported by observations, but the physical cause remains unknown. It may be a constant property of empty space. It may be a field that slowly changes. It may indicate that our understanding of gravity is incomplete. Cosmic voids respond strongly to the expansion history because they contain little matter to resist it. Their sizes, shapes, and growth rates may therefore help reveal whether dark energy has remained constant across time. Future surveys will map millions of galaxies across vast cosmic volumes. Astronomers will compare the observed void population at different distances. Because distant light comes from earlier times, this will allow them to study how voids evolved over billions of years. A nearby void shows the modern universe. A distant void shows the universe when it was younger. Together, they form a sequence through cosmic history. Scientists can ask whether voids expanded at the rate predicted by a cosmological constant. They can examine whether galaxies flowed toward their boundaries as expected. Even a tiny difference could matter. But cosmic measurements are rarely simple. The observed shape of a void depends on both geometry and motion. Galaxies have their own velocities in addition to the general expansion. The method used to identify voids can also change the results. Researchers must carefully model all these effects. The work may sound technical, but the central idea is simple. The emptiness changes with time. By measuring that change, we learn how the universe itself expands. Another mystery lies in the connection between voids and the earliest universe. The cosmic web grew from tiny density variations visible in the cosmic microwave background. But connecting a particular modern void to a particular early fluctuation is extremely challenging. Matter has moved. Voids have merged. Filaments have grown. The modern structure has been shaped by nearly 14 billion years of gravitational evolution. Computer simulations act as bridges between the beginning and the present. Scientists create virtual universes using different assumptions about dark matter, dark energy, gravity, and galaxy formation. They allow these universes to evolve and then compare the results with observations. A successful model should produce not only the correct number of clusters and galaxies, but also realistic voids. The voids should have the right sizes. Their density profiles should match. Their galaxies should contain the correct amounts of gas and stars. Their dwarf populations should resemble what telescopes find. If one model succeeds across all these tests, confidence in it grows. If it fails, Scientists adjust the physics or improve the way complex processes are represented. Star formation is particularly difficult to simulate. A cosmological simulation may cover billions of light-years, while individual stars form inside clouds measured in light-years or less. No single calculation can easily represent every scale in full detail. Researchers therefore use simplified rules based on smaller simulations and observations. These rules describe when gas forms stars and how stellar energy affects the surroundings. A small change in these assumptions can alter the number and brightness of dwarf galaxies. This is why void galaxies are such demanding tests. Their weak gravity makes them highly sensitive to feedback. One burst of supernovae can remove much of their gas. Ultraviolet radiation can stop star formation in a tiny halo. A slightly more massive halo may retain enough material to shine. The boundary between a dark halo and a visible dwarf galaxy can depend on a delicate balance. Finding that boundary is essential for understanding why some structures light up while others remain dark. Black holes present another hidden question. How common are central black holes in dwarf void galaxies? If many isolated dwarfs contain them, the result could reveal how black hole seeds formed in the early universe. One theory suggests that the first massive stars collapsed into black holes. Another proposes that enormous gas clouds collapse directly, creating heavier seeds. In crowded environments, repeated mergers and feeding can erase evidence of the original seed. A black hole in an isolated dwarf may have grown very little. Its present mass could therefore remain closer to its ancient beginning. But finding a quiet black hole is difficult. A black hole emits no light by itself. It becomes visible only when surrounding material falls inward and heats up. If little gas reaches the center, the black hole can remain hidden. Sensitive X-ray and radio observations may reveal faint activity. The motion of stars near the center can also provide evidence, but the distances involved make this challenging. Some void galaxies may contain ancient black holes that have remained silent for billions of years. They are cosmic fossils we have not yet learned to see clearly. The possibility of planets and life in void galaxies adds another layer of wonder. Can metal-poor environments form rocky planets efficiently? Observations show that planets can form around stars with a range of chemical compositions, but the abundance and types of planets may differ. Gas giants may be more common around metal-rich stars because their solid cores can form more quickly. Small rocky planets may require fewer heavy elements, although they still need materials such as iron, silicon, oxygen, and carbon. A void galaxy with slow chemical enrichment could gradually become more favorable for planet formation. Its earliest stars may have had few rocky companions. Later generations could form richer planetary systems. Life, if it appeared, might arise long after the galaxy's first stars. Isolation would not prevent biology. A planet does not need a nearby galaxy to have oceans, chemistry, or sunlight. Its local star and planetary environment matter far more. Yet galactic conditions can influence radiation, element abundance, and the frequency of catastrophic events. A void galaxy may experience fewer nearby supernovae and less disturbance from major mergers. This could provide long periods of stability. On the other hand, low metallicity might reduce the supply of planet-building material. The balance is uncertain. We currently have no way to detect life in another galaxy, especially one located deep inside a void. Even identifying individual planets there is beyond most present techniques. But the physical possibility remains. A small world may orbit a red dwarf in an isolated galaxy while the nearest large spiral lies millions of light-years away. Its sky would contain local stars and an almost endless outer darkness. If life looked upward from such a world, it might ask the same questions we do. Where did everything come from? What exists beyond the darkness? Are we alone? Cosmic isolation can change the view, but not the curiosity. Future observatories may answer many void mysteries. Wide-field optical telescopes will repeatedly image large portions of the sky, revealing faint galaxies and changes over time. Radio arrays will map hydrogen across unprecedented volumes. Space telescopes will study infrared light from old stars hidden beneath bright young populations. X-ray observatories will search for hot gas and quiet black holes. Gravitational wave detectors may eventually hear mergers involving black holes from dwarf galaxies. Each instrument observes a different messenger. Light, radio waves, X-rays, particle motion, and gravitational waves together create a fuller picture. No single telescope can reveal the entire void. The deepest understanding comes from combining them. A faint optical galaxy may be surrounded by a huge radio hydrogen disk. An X-ray point at its center may reveal a black hole. A spectrum may show primitive chemistry. A velocity map may uncover an unseen companion. A computer simulation may explain how all these features developed. Piece by piece, the quiet galaxy becomes a complete story. Still, some mysteries may remain for generations. Dark matter may continue to resist direct detection. Dark energy may remain an unexplained property of space. Hidden galaxies may be too faint to count completely. The centers of the deepest voids may be almost impossible to map in detail. Science does not promise that every question will be answered quickly. It offers a way to approach the unknown carefully. Observe, measure, compare, question, try again. Cosmic voids reward this patience because their signals are subtle. They do not demand attention with brilliant light. They invite it through absence. A missing galaxy becomes a clue. A weak radio whisper becomes evidence. A slight motion becomes a map of invisible gravity. An apparently empty region becomes a record of cosmic history. And perhaps this is the most relaxing fact about void galaxies. The universe can create complexity without crowding. It can build a galaxy from scattered gas inside an enormous darkness. It can preserve ancient stars in a tiny dwarf system. It can hide rivers of matter where no light is visible. Even emptiness has structure. Even isolation has history. Even darkness can contain the beginning of a star. So, for the final moments of our journey, imagine the universe as the great cosmic web. Bright clusters rest at the intersections. Long filaments curve between them. Vast voids fill the spaces in between. Now move toward the center of one of those voids. At first, everything becomes dark. Then a faint galaxy appears. Its stars turn slowly around an unseen halo. A thin stream of hydrogen approaches from the cosmic web. Several blue stars shine near its outer edge, while ancient red stars rest quietly beneath them. Farther away, an undiscovered dwarf galaxy drifts in silence. Beyond that, perhaps, a starless halo waits without light. The region is empty compared with the cluster, yet it is not lifeless or still. Gravity continues. Gas continues. Stars continue. The universe continues. And as you rest, let that lonely galaxy remain in your thoughts, a small, peaceful island of light surrounded by an ocean of deep space. It does not need to be crowded to be beautiful. It only needs enough matter, enough time, and the quiet patience of gravity.